Gaze up at the night sky on a clear, dark evening, and you might feel a sense of profound emptiness, a vast, silent ocean of black punctuated only by distant points of light. But what if I told you that space is anything but empty, that between those shimmering stars lies a mysterious, invisible realm teeming with secrets, a cosmic tapestry woven from the very fabric of creation itself? Welcome to the Interstellar Medium, a hidden universe of gas, dust, and energy that holds the answers to how stars are born, how galaxies evolve, and perhaps even how life began. It's a place of breathtaking beauty and deep enigmas, and today we're setting out to explore its 30 greatest mysteries. Picture the pillars of creation, those iconic towers of cosmic dust and gas where new stars ignite like celestial fireworks. They're not just stunning to look at, they're a window into the dynamic, ever-changing nature of the space between stars. This isn't some static void. It's a rich, complex soup of particles and forces, where temperatures range from near absolute zero to millions of degrees, and where fragile molecules drift alongside powerful radiation. It's here, in this seemingly empty expanse, that the story of our universe unfolds, a story written in the language of hydrogen clouds, cosmic rays, and stardust. So what fills that immense darkness? How does something so diffuse shape the fate of galaxies and the birth of solar systems? And what secrets does it hold about our own place in the cosmos? Over the course of this journey, we'll uncover the astonishing truths behind the interstellar medium, from its role in creating the building blocks of life to its influence on the largest structures in the universe. This is more than a tour of cosmic curiosities. It's an invitation to see the universe in a whole new way, to peer into the hidden machinery of space and time. So settle in, open your mind to wonder, and let's begin our exploration of the 30 mysteries that make the interstellar medium one of the most fascinating frontiers in all of science. Our journey into the interstellar medium begins with one of its most fundamental and beguiling components, cosmic dust. These are not the fluffy accumulations you might find under your bed, but microscopic grains of carbon and silicate finer than smoke that drift through the vast expanses between stars. They are the architects of shadow and light in our galaxy, dimming the brilliance of distant suns and painting dark nebulas across the Milky Way. But their most critical role is as the primordial building blocks of planets and even life itself. So where does this essential, universe-shaping material actually originate? The leading theory points to the final, dramatic chapters in the lives of stars. Picture a massive, aging red giant star having exhausted the hydrogen fuel in its core. As it swells and cools, complex chemical reactions begin in its extended atmosphere. In these relatively calm, cooler outer layers, atoms like carbon, silicon, and oxygen gently bump into one another, sticking together and gradually building up tiny specks of solid matter. These nascent dust grains are then carried away on powerful stellar winds, streaming out into the void to eventually mingle with the interstellar medium. It's a slow, beautiful, and almost poetic process, a star spending its dying breath seeding the galaxy with the ingredients for new worlds. But there is another, far more violent birthplace for stardust. When a massive star ends its life not with a whisper but a cataclysmic bang as a supernova, the unimaginable energy and pressure unleashed in that explosion can forge heavy elements and dust in mere moments. The supernova's ejector, a blazingly hot cloud expanding at incredible speeds, provides a chaotic crucible where atoms are forced together, creating a rich cocktail of new dust grains that is then hurled across light years. This method is fast and exceptionally productive, potentially generating entire solar systems worth of raw material in a single event. The great cosmic detective story now revolves around determining which of these sources is the true dominant contributor. The challenge is immense. Observing these formation processes directly is like trying to watch a single snowflake form in a blizzard from thousands of miles away. Astronomers must instead rely on subtle clues. They analyze the light from distant clouds, looking for the unique chemical fingerprints of different dust compositions that might hint at their origin. They study the remnants of ancient supernovae with powerful telescopes, searching for telltale signs of freshly synthesized dust, and they create complex computer models to simulate the physics of both stellar winds and supernova shocks. The current evidence suggests a fascinating answer. Both mechanisms are likely at work, contributing to a grand cosmic cycle. The gentle, continuous output from red giants might provide a steady trickle of dust, while the occasional supernova delivers enormous, game-changing injections. This ongoing debate is more than academic. It gets to the very heart of how our own planet and every rocky world we've ever discovered came to be. The iron in our blood and the silicon in the rocks beneath our feet were once part of this enigmatic dust, and its origin story is, in a very real sense, our own. Now, as we move from the solid grit of cosmic dust, we encounter something far more complex and strangely familiar floating in the void: vast, invisible clouds of organic molecules. If you've ever caught the scent of a barbecue or smelled the distinct aroma of a car starting on a cold morning, you've already had a close encounter with a class of compounds known as polycyclic aromatic hydrocarbons, or PAHs. These are not simple molecules. They are sprawling, carbon-based structures like microscopic patchworks of hexagons, and they are absolutely everywhere in the interstellar medium. They are so abundant, in fact, that they are considered a major component of cosmic carbon, and they account for a significant portion of the organic material in our galaxy. We know they're out there not because we can see them directly, but because they leave a unique calling card in the infrared spectrum. When these molecules are warmed by starlight, they vibrate in a specific way, emitting a set of faint but unmistakable infrared signals that our telescopes can detect. It's like every pH molecule in the universe is humming the same distinct tune, and astronomers have become expert listeners. This infrared signature has been found in the most unexpected places: in the swirling debris around distant stars, in the diffuse clouds of the interstellar medium, and even in other galaxies. Their presence is a universal constant, a faint, organic haze permeating the cosmos. Yet for all their abundance, their exact identity remains one of the great chemical mysteries of space. The infrared signature tells us the general family of molecules we're dealing with, but it's like hearing a large choir from a great distance. You can tell they're singing, but you can't make out the individual words or identify every single voice. We don't know the precise molecular structures of these space-borne PAHs. Are they relatively small and simple, or are they enormous, complex networks of carbon atoms? This question is crucial because their structure determines their stability and their potential role in the chemistry of life. This leads to another, even more profound puzzle: their resilience. The interstellar medium is a brutally hostile environment, flooded with intense ultraviolet radiation from hot stars that should tear complex organic molecules like these to shreds. And yet, PAHs not only survive but appear to thrive. How do they withstand this constant barrage? Some scientists theorize their multi-ringed structure makes them exceptionally durable, like a well-built honeycomb that can absorb and dissipate energy. Others suggest they might be forming and reforming constantly inside protective pockets of ice on dust grains, achieving a kind of immortality through continuous rebirth. Their stubborn persistence challenges our understanding of chemistry in extreme conditions, which brings us to the most captivating question of all: are these hardy, abundant molecules among the fundamental building blocks of life? The possibility is astonishing. We know that PAHs are present in meteorites that have fallen to Earth, and they are rich in carbon, the essential element for life as we know it. In the chaotic environments of protoplanetary disks, where new planets are coalescing, these robust molecules could have been incorporated into asteroids and comets. These celestial bodies then could have delivered this organic cargo to the surface of early Earth, seeding our young planet with the probiotic ingredients necessary for life to eventually emerge. The faint infrared hum we detect from deep space might be the faint echo of our own chemical origins, a suggestion that the universe is not only capable of creating life, but is actively and everywhere preparing the groundwork. While we now know the interstellar medium is filled with the chemical signatures of familiar molecules, it also holds a far deeper secret, a series of cryptic messages written in light that have resisted deciphering for over 100 years. If you were to take the light from a distant, bright star and split it into a full rainbow spectrum, you would notice something peculiar. Scattered across that rainbow are hundreds of tiny, dark lines where specific colors of starlight have gone missing. Some of these lines are like old friends to astronomers, the unmistakable fingerprints of common elements like hydrogen, helium, and sodium, but many others are complete strangers. These are the diffuse interstellar bands, or DIBs, and they represent one of the longest-standing unsolved puzzles in all of astrophysics. These bands are not rare or faint anomalies, they are pervasive. Wherever astronomers point their spectrographs, if the starlight has passed through even a modest cloud of the interstellar medium, these dark lines appear. They are the spectral equivalent of finding hundreds of distinct, unknown fingerprints at every single crime seen across the galaxy, with no matches in any database. Their very persistence tells us that whatever is causing them is both incredibly common and remarkably stable, able to withstand the harsh conditions of space for eons. Yet, despite a century of painstaking observation and analysis, the specific molecules responsible for the vast majority of these bands remain utterly unknown. They are the interstellar medium's true anonymous substances. The quest to identify them is a monumental scientific challenge that bridges the gap between the immense scale of astronomy and the microscopic precision of chemistry. It is a classic needle in a haystack problem, but the haystack is the entire galaxy, and the needle is a single molecule. The process begins with astronomers meticulously measuring the exact wavelength of each dark line, cataloging its depth and shape with incredible accuracy. This data provides the precise lock for which chemists must then find the key. The leading candidates are large, complex carbon-based molecules, likely similar to the PAHs we just discussed, but far more elaborate. The theory is that these molecules are so large and complex that their electronic structures can absorb light at very specific, unique wavelengths, creating those dark bands we observe. But proving this theory requires recreating the impossible conditions of deep space inside a laboratory on Earth. Chemists must first synthesize a candidate molecule they suspect might be the culprit, a difficult task in itself for large, exotic carbon chains. Then they must isolate it in a vacuum chamber, cool it to temperatures just a few degrees above absolute zero, and zap it with a precise laser to see how it absorbs light. They are essentially trying to measure the shadow of a single, frozen molecule. The goal is to see if its absorption signature exactly matches just one of the hundreds of known DIBs. Even a mismatch of a minuscule fraction of a nanometer is enough to rule a candidate out. After decades of work, the scientific community has celebrated only a handful of definitive successes. In a breathtaking achievement after nearly a century of searching, one family of molecules known as Buckminster fullerenes, or carbon-60, was finally confirmed to be responsible for several specific DIBs. These are soccer ball-shaped cages of carbon atoms, and their identification was a triumph that validated the entire painstaking process. But for every success like this, hundreds of other DIBs remain stubbornly anonymous. Each unidentified band is a testament to a molecule that is abundant enough to be seen across the galaxy, yet so alien to our earthly experience that we cannot yet conceive of its structure. This enduring mystery touches on something profound about our place in the universe. The very stuff that fills the space between stars, the material that will one day form new solar systems and planets, is composed in part of substances that are completely unknown to science. It is a humbling reminder that for all we have learned about the cosmos, fundamental discoveries are still waiting to be made, hidden in the faint, dark lines starlight leaves behind as it travels through the void. Yet for all the success in identifying some of these mysterious spectral bands, another type of signal from the interstellar medium has proven even more baffling, one that wasn't hiding in starlight but in the faint, cold glow of the entire sky. To truly appreciate our next mystery, we have to rewind to the 1960s when astronomers were engaged in a monumental quest to find the faint afterglow of the Big Bang itself, the cosmic microwave background. This relic radiation would be the ultimate proof of our universe's hot, dense beginning, a whisper of creation frozen in time and stretched by the expansion of the universe into the microwave part of the spectrum. The hunt was on to detect this incredibly faint signal, a uniform glow bathing all of space, but the cosmos is full of tricks. As radio astronomers scanned the heavens, they did indeed find a microwave background, but it wasn't perfectly clean. There were anomalies, tiny patches of excess emission that didn't fit the smooth, predictable pattern they expected from the primordial glow. At first, these were dismissed as mere noise or interference, perhaps from our own galaxy. But as our instruments grew more sensitive, this anomalous microwave emission, or a ME, refused to go away. It was a real, pervasive signal, a faint hiss of microwaves that seemed to come from specific dusty regions of our galaxy where new stars were forming. The shocking realization was that the interstellar medium itself was generating its own microwave glow, creating a foreground fog that astronomers had to peer through to see the true cosmic microwave background. It was like trying to listen for a single, distant flute in an orchestra hall where the walls themselves were humming. So what in the universe could be causing this? The best hypothesis we have is as astonishing as it is strange: spinning nanodiamonds. Imagine trillions upon trillions of microscopic diamonds, each smaller than a virus, scattered throughout these cosmic clouds. As they are jostled by collisions or energized by starlight, these tiny carbon crystals begin to spin at breathtaking rates, billions of rotations per second. This rapid rotation causes them to emit radiation, and for a specific size and type of particle, that radiation falls right in the microwave band we observe. It's a remarkable idea that the cold darkness of space might be filled with a glittering, invisible fog of diamond dust humming with an energetic spin. But nanodiamonds aren't the only candidate. Other scientists point to polycyclic aromatic hydrocarbons, those same large organic molecules we discussed earlier. Their theory suggests that these floppy, asymmetric molecules don't just vibrate, they too can be set spinning by the faintest whisper of energy, and that motion could also generate the anomalous microwave signal. The problem is that we cannot yet definitively prove either mechanism. We can't simply fly a probe into a distant nebula and scoop up a sample to check for diamonds under a microscope. Instead, astronomers are forced to play a high-stakes game of indirect detection, using the precise details of the microwave emission, its intensity, its polarization, how it changes across different frequencies, to try and match it to laboratory models of how these hypothetical particles should behave. This isn't just an academic curiosity, it's a serious complication for our understanding of the cosmos. The presence of a ME means that maps of the cosmic microwave background, our most important window into the infant universe, are contaminated. Before cosmologists can decode the secrets of the Big Bang from that primordial light, they must first carefully identify and subtract out every last bit of this local microwave pollution from the interstellar medium. If they get it wrong, if they mistake this spinning dust for a feature of the early universe, It could lead to profoundly incorrect conclusions about the fundamental properties of our cosmos, like its age, composition, and ultimate fate. The hunt for the source of anomalous microwave emission is therefore more than a puzzle about dust. It is a critical cleanup operation, essential for seeing the true picture of our universe's beginning clearly. Yet for all the mysteries held in light and microwaves, the interstellar medium conceals its grandest designs within vast, shadowy structures that serve as the cradles of creation itself. Drifting through the spiral arms of galaxies like our Milky Way are immense cosmic nebulae known as molecular clouds. These are not the wispy, ethereal veils we often see in telescope images. They are the coldest, densest regions of the interstellar medium, colossal fortresses of gas and dust so thick they can blot out the light of the stars behind them for light years. It is within these frigid, dark nurseries that the universe quietly goes about the business of building new stars and solar systems. But the very existence of these clouds is a puzzle, a delicate and seemingly impossible balancing act played out on an epic scale. The central conundrum is one of stability. A molecular cloud is a place of opposing forces caught in a perpetual tug of war. On one side, you have the relentless pull of gravity, which constantly tries to crush the cloud inward to compress its gas and dust into ever denser knots that will eventually ignite as protostars. This gravitational collapse is the essential first step in star birth. But if gravity were the only force at work, these clouds would collapse catastrophically and form stars in a sudden, universal burst, which is not what we observe. Instead, these clouds persist for millions of years, forming stars at a slow, measured pace. Something must be holding gravity back, providing enough support to keep the cloud in a state of fragile equilibrium for eons. So what are these mysterious forces propping up these cosmic giants? One key player is internal gas pressure. The molecules inside the cloud, though extremely cold, are still in motion, bouncing off one another and creating an outward pressure that resists collapse. Think of it like a vast balloon. The air molecules inside push outward on the rubber skin. In a molecular cloud, this thermal pressure acts as a cushion against gravity's crush. But in the deepest, coldest cores of these clouds, where temperatures can plummet to just 10 degrees above absolute zero, this thermal pressure becomes incredibly weak. It alone cannot explain how these regions remain stable. This is where more exotic forms of support must enter the picture. Astronomers now believe the answer is woven through the clouds on an invisible tapestry of magnetic fields. These fields are believed to be frozen into the ionized part of the gas, creating a network of powerful lines of force that thread through the entire structure. Imagine the cloud being filled with countless invisible strands of elastic. As gravity tries to pull material inward, it must also drag these magnetic field lines along, bending and stretching them. The fields fight back, creating a magnetic pressure that can effectively stiffen the cloud, providing a powerful support structure that holds everything up. It's as if the cloud has a skeleton made not of bone but of pure energy. The strength and configuration of these magnetic fields are now thought to be the primary governor that determines how fast a cloud can collapse and how many stars it can form. But there's another disruptive force at work: turbulence. Far from being serene, placid pools of gas, molecular clouds are chaotic maelstroms. They are stirred by shock waves from nearby supernova explosions, sculpted by the fierce stellar winds from massive young stars, and roiled by their own internal motions. This turbulence creates complex swirls and eddies within the gas, which can also provide support against collapse by constantly shuffling material around. It acts like a chaotic whirlwind, keeping dust particles aloft. The ongoing mystery for astrophysicists is to understand the precise recipe of this cosmic cocktail. What is the exact mix of gravity, magnetic fields, gas pressure, and turbulence that determines a cloud's fate? Supercomputer simulations that try to model all these forces simultaneously are some of the most complex in all of science. and they are our best tool for watching this cosmic dance play out over millions of years. While physicists grapple with the large-scale forces shaping these clouds, chemists are utterly fascinated by the astonishingly complex reactions taking place in their frozen hearts. The interior of a dark molecular cloud is one of the most hostile environments imaginable for chemistry. Temperatures barely above absolute zero and densities that are practically a vacuum by Earth standards. In such a place, you would expect chemistry to grind to a complete halt. Atoms and molecules should move too slowly to ever meet and react, and yet the opposite is true. These clouds are veritable factories for complex molecules. Radio telescopes have identified over 200 different molecular species in these regions, from simple carbon monoxide to startlingly complex organic compounds like ethyl alcohol, acetic acid, the key component in vinegar, and even simple sugars like glycoldehyde. This raises a thrilling question: how can such sophisticated chemistry occur in a deep freeze? The secret seems to lie on the surface of those same microscopic dust grains we discussed earlier. In the near-perfect vacuum of a molecular cloud, a lone gas atom might wander for centuries before bumping into another one, but it will eventually collide with a dust grain and stick to its surface. This grain acts as a tiny laboratory bench, holding atoms and molecules in place long enough for them to meet and form a bond, a process that would be impossible in the open gas. The incredibly cold temperature of the grain is actually an advantage here. It prevents the newly formed molecule from immediately shaking itself apart. Over millennia, these grains can become coated in a mantle of icy water, carbon monoxide, and other simple molecules, which then act as a site for even more complex reactions, perhaps even creating the precursors to amino acids. This discovery fundamentally changes our understanding of these stellar nurseries. They are not just gravitational factories for stars, they are also chemical reactors that are pre-processing the raw ingredients for planets and life. The alcohol and sugar molecules forming in these clouds will eventually be incorporated into the next generation of stars and the protoplanetary disks that swirl around them. When a new solar system forms, these complex organic molecules are already present, baked into the comets and asteroids that will later deliver them to the surfaces of young planets. The very building blocks of biology may have their origins in the silent, dark chemistry of these cosmic clouds long before our sun even flickered to life. The physics of molecular clouds thus weaves together the grand destiny of stars with the intimate beginnings of life itself, all within their dark and swirling embrace. We have explored the cold, chaotic nurseries where stars are born, but there is an invisible architect at work within those clouds, a force that guides their collapse and shapes their very structure. This brings us to our sixth mystery, one that weaves through the entire interstellar medium yet remains incredibly elusive: the galactic magnetic field. Imagine an immense, invisible web of force lines stretching between stars and threading through every nebula. This is not a science fiction concept. It is a very real, fundamental component of our galaxy. Despite its pervasive influence, this magnetic field is fantastically difficult to measure, and its true strength and configuration are among the most significant unsolved problems in modern astrophysics. So how do we even begin to detect something that is, by its very nature, invisible? Astronomers must become detectives of light, looking for subtle clues imprinted on the radiation that passes through the magnetized medium. One of the most powerful techniques relies on a property of light called polarization. As starlight travels through clouds filled with elongated, spinning dust grains, something remarkable happens. These microscopic grains tend to align themselves with the local magnetic field, like countless tiny compass needles all pointing in the same direction. When light hits these aligned grains, it is scattered and becomes polarized, meaning its waves oscillate in a preferred direction parallel to the field lines. By carefully analyzing this polarized starlight or the polarized emission from the dust itself, we can literally map the magnetic field's orientation across vast distances, tracing the ghostly outline of the galaxy's hidden skeleton. Another method involves a phenomenon known as the Zeeman effect. When atoms are located within a magnetic field, the energy levels of their electrons shift slightly. This causes the spectral lines they emit to split into two or more components, a telltale splitting that is directly proportional to the strength of the field. Detecting the Zeeman effect is like taking the magnetic field's fingerprint, but it is an exceptionally challenging measurement. The splitting is incredibly tiny, requiring exquisitely sensitive radio telescopes to observe it, and even then, it is only detectable in the densest regions of gas. These painstaking observations have revealed that magnetic field strengths can vary dramatically from a few microgauss in the diffuse interstellar medium, millions of times weaker than Earth's magnetic field, to significantly stronger values within dense molecular clouds. Why does this faint cosmic magnetic field matter? Its influence is absolutely profound. Within those stellar nurseries we discussed, the magnetic field is a primary regulator of star formation. It provides crucial support against gravitational collapse, effectively propping up a cloud and slowing down the birth of new stars. The field acts like a cosmic scaffolding, channeling flowing gas and guiding it into filamentary structures, which in turn fragment into the cores that will become stars. Without this magnetic support, clouds would collapse far too quickly, resulting in a violent burst of star formation that would rapidly exhaust a galaxy's fuel. The magnetic field ensures star birth is a slow, sustained process governing the very rhythm of galactic evolution. Its role doesn't end there. The galactic magnetic field is also the ultimate cosmic ray highway. Cosmic rays are high-energy particles, mostly protons and atomic nuclei, that streak across the galaxy at nearly the speed of light. But without a guide, these charged particles would travel in straight lines and quickly escape the galactic disk into the emptiness of intergalactic space. The magnetic field prevents this. Its lines of force trap the cosmic rays, causing them to spiral around the field lines in a tight helix. This effectively confines them to the galaxy, forcing them to bounce around for millions of years before eventually finding an escape route. This magnetic containment is why we detect such an abundance of cosmic rays, and it directly influences the radiation environment throughout the interstellar medium, which in turn can impact the chemistry of forming planetary systems. Understanding the origin and large-scale structure of this field is the final piece of the puzzle. The prevailing theory is that it is a self-sustaining dynamo, much like the one that generates Earth's magnetic field but on a galactic scale. It is thought that the slow, differential rotation of the galaxy itself, the fact that the inner regions rotate faster than the outer ones, could stretch and wind up a weak primordial magnetic field, amplifying it over billions of years. Turbulent motions from supernova and stellar winds would then twist and tangle this field, creating the complex web we infer today. However, the initial seed field that started this entire process remains a complete mystery. Was it generated in the early universe during its initial moments of inflation? Or was it born later from the turbulent actions of the first stars and galaxies? We simply do not know. This invisible force which sculpts gas, guides particles, and steers the evolution of the galaxy retains the secret of its own birth, a fundamental power whose origins are still hidden in the dark. This delicate thermal equilibrium is the master switch for star formation itself. In the coldest, densest cores of molecular clouds where cooling processes win out, the gas pressure plummets. This low pressure can no longer fight back against the relentless crush of gravity, allowing those dense knots of gas and dust to collapse inward and begin their long journey to becoming protostars. Conversely, in regions where heating dominates, perhaps because a nearby hot star is flooding the area with ultraviolet radiation, the increased thermal pressure prevents collapse, effectively putting up a no star formation sign and keeping the cloud puffed up and diffused. This constant, invisible battle between heating and cooling is what dictates the rhythm of galactic evolution, determining where and when new suns will ignite to light up the darkness. After exploring the invisible forces of galactic magnetism and the delicate thermal balance of the interstellar gas, we arrive at a framework that attempts to bring order to this cosmic chaos. The interstellar medium is not a monolithic fog, it's a dynamic, multi-layered ecosystem. To make sense of its complexity, astronomers have developed the three-phase model, a powerful but still imperfect map of this vast territory. This model proposes that the ISM exists in three distinct states or phases that coexist in a fragile, swirling balance: the searing heat of ionized gas, the mild temperatures of neutral hydrogen, and the frigid depths of molecular clouds. It's a cosmic cocktail of matter, each ingredient kept separate yet perpetually influencing the others. The first and most voluminous phase is the hot ionized medium, or HIM. This isn't a gentle warmth, it's a tenuous plasma heated to millions of degrees by the shockwaves from supernova explosions. Imagine a bubble bath on a galactic scale, where each bubble is a cavity of this incredibly hot, low-density gas blown clear by a dying star's final detonation. This phase is so energetic that atoms are stripped of their electrons, creating a soup of positively charged ions and free-flying electrons. It fills up to 80% of the volume of the galactic disk, a vast, invisible ocean in which all the other phases float like islands. Its intense heat generates enormous pressure, which helps to contain and shape the cooler clouds around it, preventing the entire interstellar medium from collapsing under its own gravity. In stark contrast floats the warm neutral medium, or WNM. This is the ISM's great transitional zone, a fog of atomic hydrogen gas with temperatures measured in thousands, not millions of degrees. Here, atoms are mostly whole, having held onto their electrons. This phase is the reservoir from which all else forms. It's not dense enough to readily collapse into stars, but it's the raw material that, when compressed and cooled, will eventually feed the stellar nurseries. The warm neutral medium is constantly buffeted and heated by the same shocks and radiation that create the hot phase, but it also possesses a remarkable ability to cool itself through radiation, allowing it to maintain its distinct identity. It acts as a crucial intermediary, a bridge between the violent energy of supernova and the serene cold of star-forming regions. Finally, there are the cold, dense islands themselves, the cold neutral medium, or CNM, and the molecular clouds we've already explored. These are the regions where the warm gas has finally lost its thermal battle, cooling and condensing into dense clumps and filaments. Shielded from harsh external radiation by their own accumulating dust, these clouds become the sites of complex chemistry and ultimately gravitational collapse. The three-phase model beautifully illustrates how these states are in a constant cyclical dance. Supernova create the hot phase, which expands and sweeps up shells of warm gas. This compressed shell can then cool, fragment, and condense into the cold phase, which then forms stars. Those massive stars then live short, violent lives and explode as supernova, once again reheating the surrounding space and beginning the cycle anew. It's the great cosmic recycling program, with the ISM as both the factory and the product. Yet for all its explanatory power, the three-phase model is almost certainly an oversimplification. As our observations become more precise, astronomers are discovering regions of the ISM that don't fit neatly into these three boxes. There are pockets of gas with intermediate temperatures and densities that challenge the clear boundaries between phases. There is also the growing mystery of the so-called dark gas, a component that radio telescopes struggle to see directly. We infer its existence because we see the effects of its dust blocking starlight and its presence influencing cosmic rays, but the gaseous hydrogen itself is frustratingly elusive. This dark gas might represent a substantial mass of molecular hydrogen that forms on the surfaces of dust grains but, lacking a dipole moment, doesn't emit the radio waves we typically use to detect it. Its existence suggests there could be an entire hidden geography within the ISM that our current maps fail to chart. This leads to a profound question. Is the three-phase model complete, or are we missing entire chapters in the story of the interstellar medium? Some theorists propose the existence of a fourth, even more exotic phase, a mist of tiny, cold clouds of neutral hydrogen, each too small and faint to be detected individually with our current technology. This population of shadowy clumps could be zipping through the hot phase like a swarm of ghosts, representing a significant fraction of the galaxy's missing baryonic matter. The model, therefore, is not a final answer but a living theory. It provides the essential vocabulary and structure we need to begin understanding the ISM's complexity, but it also highlights the limits of our current knowledge. Every new observation pushes at its edges, hinting at a richer, more intricate, and even more mysterious galactic ecosystem than we ever imagined. Now, as we shift our gaze from the grand architectures of gas and magnetism, we encounter a far more transient and violent phenomenon ripping through the interstellar medium, cosmic rays. This is not a form of light or radiation in the conventional sense, but a relentless, invisible rain of atomic shrapnel. Every square centimeter of Earth's upper atmosphere is struck by several of these particles every second, a constant barrage of protons and atomic nuclei traveling at a significant fraction of the speed of light. They carry so much energy that, if their origin were visible, they would outshine the sun in our sky. They are the ultimate interstellar projectiles, and for over a century, their birthplace has been one of the most intense mysteries in astrophysics. The fundamental question is one of pure power. What natural engine in the universe is capable of accelerating a mere proton to such insane velocities, granting it energies that dwarf anything produced in our most powerful particle colliders? The leading suspect for this cosmic crime has long been the aftermath of a supernova explosion. When a massive star dies, it doesn't just fade away. It unleashes a blast wave of incandescent gas that expands outward into the interstellar medium at thousands of kilometers per second. This creates a supernova remnant, a rapidly growing sphere of shock waves and turbulent, magnetized plasma. It is within this chaotic maelstrom that physicists believe the magic happens, through a process known as Fermi acceleration, named after the brilliant Italian physicist Enrico Fermi who first proposed the mechanism. Imagine a single proton from the interstellar medium drifting near this expanding shock front. As the supersonic wave of energy passes through, it creates a violent magnetic barrier. Our proton, being electrically charged, gets caught in this tangled web of magnetic fields. It doesn't simply pass through, it bounces back and forth across the shock wave, trapped as if in a chaotic magnetic pinball machine. With each crossing, it gains a little more energy from the moving magnetic fields, a process physicists call first-order Fermi acceleration. It's like a tennis ball being repeatedly struck by a swinging racket, each hit sending it back faster than before. After countless cycles, the proton has been boosted to nearly the speed of light. Eventually, the magnetic turbulence can no longer contain it, and it escapes, fired into the galaxy like a bullet from a rifle, destined to travel for millions of years. The elegance of this theory is that it provides a perfect natural particle accelerator, powered by the most energetic events in the galaxy. It also neatly explains the sheer number of cosmic rays we detect. Supernovae are common enough to account for the relentless drizzle. However, a compelling theory is not the same as a proven fact. The challenge lies in obtaining definitive evidence, a smoking gun that directly links a specific supernova remnant to the cosmic rays we measure. We cannot simply follow a cosmic ray back to its source. Their paths are scrambled by the galaxy's magnetic fields during their long journey, making them arrive at Earth from all directions equally, masking their point of origin. So astronomers must instead look for the secondary signatures these accelerators would leave behind. When the ultra-fast protons accelerated within a remnant collide with the slower-moving gas of the interstellar medium, they should produce two very specific fingerprints, gamma rays and neutrinos. The hunt has therefore focused on using powerful telescopes to scan supernova remnants for these telltale signs of proton collisions. Some of the most exciting evidence in recent years has come from observations of remnants like Tycho's supernova and IC 443. Instruments like the Fermi Gamma Ray Space Telescope have detected high-energy gamma rays emanating from these shells, and the energy signature of that light is highly suggestive that protons are being accelerated there to cosmic ray energies. Yet, even with this supporting evidence, critical questions remain. The precise details of how the magnetic fields within the shock waves trap and energize particles are fiendishly complex and not fully understood. Computer simulations struggle to model the entire process from start to finish, and it remains unclear if Fermi acceleration alone can account for the very highest energy cosmic rays observed. Some of these particles carry energies so profound that their origin may lie outside our galaxy entirely, in far more violent extragalactic objects like active galactic nuclei. The story of cosmic rays is thus a layered mystery. While supernova remnants remain the prime suspect for the majority of these particles, the investigation is still very much open, a testament to the incredible power hidden within the turbulent aftermath of a star's death. But if supernova are the cannons firing material out of the galactic disk, gravity is the force that ensures what goes up must eventually come down. This leads us to the beautiful and aptly named galactic fountain model. Envision this: a massive star explodes in the plane of the Milky Way. The incredible energy doesn't just spread outward, it punches upward, propelling a colossal bubble of million-degree gas through the thinner layers of the interstellar medium and out, away from the star-filled disk. This hot, ionized plasma, rich with newly forged heavy elements from the supernova itself, rises high above the galactic plane, reaching thousands of light-years into the largely empty region known as the galactic halo. It doesn't escape the galaxy's gravity, though. Instead, it reaches a certain altitude, cools over millions of years by radiating away its immense heat, and then begins to condense into denser clouds. Under the steady pull of gravity, these clouds then begin their long fall back down toward the disk, plummeting through space like a celestial rainfall. This isn't a gentle drizzle, it's a downpour of enriched material returning to the galactic disk to be incorporated into the next generation of stars and planets. We are essentially watching the galaxy recycle its own material on an epic scale. The evidence for this fantastic cycle is written in the sky, but you need to know how to look for it. When astronomers train their telescopes on the regions high above the Milky Way's disk, they don't see nothingness. They find massive, faint structures of gas, some of them absorbing light from distant quasars and background stars. These are known as high-velocity clouds and intermediate-velocity clouds, and they are considered the telltale signs of this fountain in action. Some of these clouds show compositions that are low in heavy elements, suggesting they are ancient, primordial gas perhaps falling into the galaxy for the very first time. But many others show a different signature. They are enriched with those heavier elements like oxygen, silicon, and iron, the unmistakable products of supernova nucleosynthesis. This is the smoking gun. It's the chemical fingerprint of gas that was once part of the star-filled disk, was blasted out by a stellar explosion, and is now cooling and falling back home. We are literally seeing the rain clouds of the galactic fountain gathering before their descent. This grand circulatory system solves a major cosmic problem: mixing. Without a mechanism like the fountain, the galaxy would be a very segregated place. The heavy elements produced by supernova would remain locked in the dusty, dense environment of the galactic disk, leading to extreme chemical inhomogeneity. Some regions would become overly enriched, quickly using up all their gas in bursts of star formation, while others would remain pristine and barren. The fountain model prevents this. By constantly churning the galaxy's gas, it ensures that the products of stellar alchemy, the oxygen we breathe, the iron in our blood, the silicon in our rocks are thoroughly mixed throughout the interstellar medium. This process seeds the entire disk with the necessary ingredients for rocky planet formation and ultimately life. Our own solar system was likely forged from gas that had been cycled through this fountain multiple times, enriched by generations of long-dead stars. Yet for all its elegance, the galactic fountain model is fraught with unanswered questions that make it a vibrant area of modern research. The precise dynamics of the process are incredibly complex and difficult to simulate. How much mass is actually involved in each cycle? What is the exact balance between gas that escapes into the halo permanently and gas that falls back? The fate of the falling gas is particularly intriguing. When these high-velocity clouds come crashing back down onto the galactic disk, they don't do so quietly. They create powerful shocks as they slam into the thinner gas of the interstellar medium. These impacts could themselves trigger new waves of star formation, linking the death of old stars directly to the birth of new ones in a self-regulating cycle. Furthermore, the entire journey from eruption to cooling to descent takes tens of millions of years. This means the fountain operates on timescales that are long even by astronomical standards, making it a challenge to observe the full cycle in action. We are essentially seeing snapshots of the process: the blast, the rising bubbles, the hovering clouds, and the incoming rain. Piecing these snapshots together into a coherent movie of galactic evolution is one of the great ongoing endeavors in understanding our dynamic and ever-changing galaxy. For all the incredible mass we can see in galaxies and the vast structures of the interstellar medium, cosmology presents us with a deeply puzzling shortfall. When scientists add up all the ordinary matter, the protons and neutrons that make up everything from stars to people, known collectively as baryons, the numbers simply don't match. Based on precise measurements of the cosmic microwave background, which acts as a recipe book for the infant universe, we know exactly how much of this normal matter should exist. Yet, when we inventory the present-day universe, counting all the stars, galaxies, and the detectable gas between them, we come up almost 80% short. This is the missing baryon problem, a cosmic accounting error on a staggering scale that suggests most of the universe's ordinary material is hiding in plain sight. The prime suspect in this mystery is a theoretical structure known as the warm-hot intergalactic medium, or WIM. Picture the universe not as a collection of isolated galaxies, but as a single, vast cosmic web. Gravity, acting over billions of years, has pulled most matter into an immense network of filaments and nodes. The galaxies and massive clusters we see are just the densest knots in this web. Stretching between them, in the incomprehensibly vast voids, are the filaments of the WIM. This is not a dense, cold gas like a molecular cloud. It is an incredibly tenuous plasma, so diffuse that its average density might be just a few dozen particles per cubic meter. But what it lacks in density, it makes up for in volume. These filaments are so enormous that if even a small fraction of their gas is in this warm, hot state, it could easily account for all the missing baryonic matter in the universe. The warm-hot in its name is a relative term, but in this context it means something extraordinary. This gas is believed to be heated to temperatures between 100,000 and 10 million degrees. It didn't start out this hot. As matter flowed along the gravitational scaffolding of the cosmic web into the growing clusters and galaxies, it didn't always fall in smoothly. These flows created colossal shock waves, similar to the sonic boom from a jet but on a galactic scale. These shocks violently compressed and heated the gas that wasn't pulled all the way into a galaxy, leaving it stranded in these intergalactic filaments as a superheated ionized plasma. It is the universe's largest and most hidden energy sink, a reservoir of heat and matter that has, until recently, evaded all our attempts to observe it. Finding this ghostly plasma is one of the most difficult challenges in modern astronomy. Its extreme temperature means it doesn't emit significant visible light, and its incredible thinness makes it nearly transparent. Astronomers must therefore rely on incredibly clever and indirect methods to prove its existence. The most successful technique involves using the brightest beacons in the universe, quasars. These are intensely luminous galactic cores powered by supermassive black holes. By pointing our most powerful space telescopes, like Chandra and XMM Newton, at these distant quasars, we can analyze their light after it has passed through billions of light-years of space, including the proposed filaments of the WIM. The hope is to find the subtle fingerprints of highly ionized oxygen, oxygen that has been stripped of most of its electrons by the intense heat. When this specific type of oxygen lies in our line of sight, it will absorb very particular wavelengths of the quasar's X-ray light, creating a tiny dip in the spectrum that acts as a direct signature of the WIM presence. After years of searching, astronomers have begun to find these needles in a cosmic haystack. There have been a handful of tantalizing detections where the predicted absorption lines from highly ionized oxygen appear exactly where the models of the cosmic web say a filament should be. These are not dramatic images of glowing structures, they are minuscule statistical anomalies in plots of data. But each one is a monumental victory, a direct piece of evidence that the WIM is real and that it does indeed contain a vast amount of matter. Another method looks for a faint, diffuse glow of X-rays emanating from the regions between galaxies, which could be the combined emission of the entire warm hot filament. While these observations are still in their infancy, they are slowly painting a picture of a universe where the space between galaxies is not empty, but filled with a seething, invisible ocean of matter. Solving the missing baryon problem is about far more than just balancing the cosmic books. It is fundamental to our understanding of how galaxies form and evolve. This warm-hot intergalactic medium is not a static reservoir. It is the primary source of fuel for future galactic growth. Models suggest that galaxies are constantly accreting or drawing in this gas from the surrounding WIM. It is the raw material from which new stars will eventually form. Furthermore, this gas acts as a recycling system, collecting the heavy elements that are blown out of galaxies by supernovae and galactic fountains, mixing them back into the intergalactic medium, and then later redepositing them onto galaxies to enrich future generations of stars and planets. The WIM is the circulatory system of the cosmos, and by finding it, we are finally beginning to understand the complete life cycle of the ordinary matter that makes up our world and ourselves. But this journey of cosmic dust is not a one-way trip to immortality. It is a cycle of constant creation and destruction, a story written in the furnace of stars and erased by their violent deaths. The life cycle of a single dust grain is a grand epic spanning millions of years, yet its existence is remarkably fragile. To truly appreciate this, let's follow the journey of one such grain, a tiny speck of silicate forged in the atmosphere of an aging red giant star. For millennia, it rides the gentle but persistent push of the stellar wind, slowly drifting away from its birthplace and into the cold emptiness of the interstellar medium. Here, it joins a vast, swirling cloud, one of the dark nebulae that blot out the starlight in the Milky Way. For ages, it floats in this dark nursery, its surface acting as a tiny laboratory bench where simple atoms like hydrogen and oxygen meet and stick, slowly building a mantle of water ice and complex organic molecules. It is in this silent, frozen state that the grain plays its most crucial role, facilitating the chemistry that may one day lead to life. Its quiet existence is shattered when a shockwave, the echo of a supernova explosion light years away, rips through its cloud. The cloud is compressed and the delicate balance of forces that held it stable is broken. Gravity takes over and our dust grain, along with trillions of its brethren, is pulled inward toward the center of a collapsing clump. It becomes part of a swirling protoplanetary disk, a vast carousel of gas and dust circling a newborn star. Within this disk, dust grains constantly collide, sticking together in a process called accretion. They grow from microscopic specks to pebbles, then to rocks, and eventually to planetesimals, the building blocks of planets. Our silicate grain might be fortunate, becoming a permanent part of a new rocky world, a literal piece of a distant exoplanet. Its long journey, starting in the heart of a dying star, would end in the bedrock of a new world, a testament to the cosmic recycling of matter. But this is just one possible fate, and arguably a fortunate one. For many more grains, the journey is far shorter and ends in spectacular annihilation. The very radiation that allows us to see the universe is also a powerful destructive force. Intense ultraviolet light from hot, young stars can physically tear molecules apart in a process called photodissociation, blasting the icy mantles off dust grains and damaging their crystalline structure. Even more destructive are the shock waves from nearby supernovae, which can blast through interstellar clouds at speeds of thousands of kilometers per second. For a dust grain, hitting one of these shock fronts is like being caught in a cosmic sandblaster. The grain is bombarded by high-energy particles and subjected to extreme heat, causing it to sputter away atom by atom or shatter entirely into fragments. A grain that took millions of years to form can be obliterated in an instant. Its constituent atoms return to the gaseous phase of the interstellar medium, ready to one day be incorporated into a new generation of stars and dust. This cycle of creation and destruction raises a fundamental question for astronomers. How efficient is this process, and what is the net lifespan of a typical dust grain? Quantifying this life cycle is incredibly difficult because it involves tracking material across vastly different environments and timescales. We know dust is being created at a certain rate, primarily in the stellar winds of asymptotic giant branch stars and in the ejecta of supernova. We can also estimate destruction rates by studying the energy output from supernova remnants and the strength of interstellar radiation fields. But balancing this ledger is a monumental challenge. Current models suggest the average lifetime of an interstellar dust grain might be surprisingly short on cosmic timescales, perhaps only a few 100 million years. This implies the dust we see in galaxies today is not primordial. It is the product of continuous and ongoing reprocessing. The galaxy must be constantly replenishing its dust supply to account for the rapid destruction, meaning the cycle we are witnessing is not a relic of the past but a vibrant and active process shaping the galactic ecosystem. The implications of this life cycle extend far beyond the dust itself. Since dust grains are the primary building blocks of planets, the efficiency of this cycle directly influences the rate of planet formation across the galaxy. If dust is destroyed too quickly, it may not have time to coagulate into planetesimals, potentially limiting the number of rocky worlds that can form. Furthermore, dust plays a critical role in the cooling of molecular clouds. Without enough dust to radiate away heat, clouds might not be able to collapse efficiently to form new stars in the first place. The life cycle of dust is therefore woven into the very fabric of galactic evolution, a feedback loop where the birth of stars creates dust, whose presence then governs the birth of the next generation of stars and planets. Understanding the timescales of this cycle is key to unraveling the story of how galaxies evolve from pristine clouds of gas into the complex, dusty, planet-filled systems we see today. Just when we think we're starting to grasp the chemistry of the interstellar medium, it throws us a curveball so confounding it has its own name, the CH+ problem. This mystery revolves around a simple-sounding molecule, the methyladinium cation, which is essentially a carbon atom bonded to a hydrogen atom with a positive charge. You wouldn't think such a basic molecular ion could cause such a fuss, but its sheer abundance in the wrong places has stubbornly defied explanation for decades, pointing to hidden fires burning in the cold depths of space. Astronomers first detected the spectral signature of CH+ in what are known as diffuse interstellar clouds. These are not the dense, cold stellar nurseries we've discussed. They are the thin, wispy veils of gas that float throughout the galactic disk, letting starlight pass through with relative ease. Their environment is typically calm and frigid, with temperatures hovering around 100 degrees above absolute zero. In such a chill, chemistry is supposed to be a slow, sedate process governed by reactions on the surfaces of dust grains. But CH+ doesn't play by these rules. Forming this molecule in the gas phase is like trying to light a match in a freezer. It requires a significant injection of energy. The most efficient way to create it is through a reaction between carbon atoms and molecular hydrogen, but this process has a formidable energy barrier. It needs either very high temperatures, around 1000 degrees Kelvin, or incredibly violent turbulence to smash the particles together with enough force to overcome their natural resistance. According to every standard model of these clouds, neither of these conditions should exist there. It's the chemical equivalent of finding a steaming cup of coffee in the middle of the Antarctic. So how does this molecule exist in such abundance? The leading theory suggests that the diffuse clouds are not the serene, placid environments we once thought. Instead, they might be riddled with tiny, localized regions of intense heat and chaos. Think of a mostly calm lake, its surface smooth and still. But just beneath that surface, there could be powerful, churning whirlpools and jets of hot water from hidden geothermal vents. Astronomers suspect similar phenomena within these gas clouds. The immense turbulence could be generated by shock waves propagating from distant supernovae, which travel for light years and can suddenly dump enormous energy into a calm region of gas, heating it violently for a short period. Alternatively, the sheer turbulence could come from the stellar winds of massive stars tearing through the cloud, stirring it into a froth and creating microscopic pockets of frictional heating where molecules are forged in these brief, intense maelstroms. Another compelling idea involves the dissipation of turbulence itself. As large-scale motions in the gas break down into smaller and smaller eddies, the energy has to go somewhere. At the very smallest scales, this energy could be converted into heat through a process called viscous dissipation, creating transient hotspots exactly where they are needed to fuel these endothermic reactions. It's a process that is notoriously difficult to model, as it requires understanding physics across a vast range of scales, from the size of the cloud down to the movements of individual atoms. This makes the CH+ molecule more than just a chemical anomaly. It is a tiny thermometer and a turbulence detector. Its presence is a direct proxy for energetic processes that are otherwise almost impossible to observe directly, telling us that what looks like a calm sea of gas from a distance is actually a seething, dynamic environment if you could zoom in close enough. Cracking this mystery is crucial because it forces us to fundamentally rewrite our models of interstellar chemistry. We can no longer assume uniform conditions within a cloud. Instead, we must account for a messy, unpredictable landscape filled with gradients of temperature and density. The energy required to form CH+ has to come from somewhere, and finding its source will reveal new details about how energy is transferred and dissipated across the galaxy. This isn't just about one molecule, it's about accurately mapping the hidden thermodynamics of the cosmos, understanding how the violent deaths of stars can influence chemistry light years away, and accepting that the interstellar medium, even in its most diffuse form, is a place of constant, energetic transformation. This relentless, often invisible churning is the engine of the interstellar medium, a force of chaos that somehow creates order. We call this phenomenon interstellar turbulence, and it is nothing like the gentle eddies in a stream or the swirl of cream in your coffee. This is gas moving at supersonic speeds, creating fractal patterns of whirls within whirls that stretch across light years. It is a storm without rain, a hurricane without an eye, a fundamental state of being for the matter between stars. This turbulence is not just a fascinating side effect. It is a primary architect of the galactic ecosystem, shaping everything from the birth of stars to the distribution of the elements that make up our world. Yet for all its importance, its origins and its ultimate fate remain deeply mysterious. To grasp the sheer power of this phenomenon, imagine flying through a molecular cloud. You wouldn't glide smoothly through a thin haze. You'd be violently tossed about by gusts of hydrogen gas moving at tens of thousands of kilometers per hour. These are not gentle breezes but supersonic shock waves that can compress gas into dense filaments or tear apart nascent stellar nurseries. This constant, chaotic motion plays a critical dual role. On one hand, it provides essential support against gravity's relentless pull. The jostling and buffeting of turbulent eddies act like a cosmic pressure, propping up vast clouds and preventing them from collapsing into stars all at once. This ensures star formation is a slow, sustained process rather than a single, catastrophic burst that would quickly exhaust a galaxy's fuel. At the same time, turbulence is a superb cosmic mixer. As it churns the interstellar medium, it thoroughly blends the heavy elements forged in supernovae, the oxygen, iron, and carbon essential for planets and life throughout the galactic gas, ensuring that new solar systems are born from well-mixed, enriched material. The central question, then, is what gigantic engine could possibly power this galaxy-wide chaos? Where does all this incredible energy come from? Astronomers have several prime suspects, each a colossal force of nature. The leading candidate is the supernova, the titanic explosion that marks the death of a massive star. A single supernova detonation releases as much energy in a few months as our Sun will over its entire 10 billion-year lifetime. A significant fraction of that energy is converted into a powerful shock wave that expands outward for centuries, plowing into the surrounding interstellar gas like a bulldozer, stirring it into a frenzy and injecting it with turbulence on a massive scale. Given that supernovae occur every few decades in a galaxy like our Milky Way, they could provide a steady drumbeat of energetic input, constantly restocking the turbulence that would otherwise slowly dissipate. But supernovae are not the only players. There is also the tremendous feedback from star formation itself. Young, massive stars are incredibly violent actors. They flood their surroundings with intense ultraviolet radiation that heats and ionizes the gas, creating vast, expanding bubbles of hot plasma. They also unleash powerful stellar winds, streams of charged particles moving at millions of kilometers per hour that can carve out cavities and drive shock fronts into the surrounding clouds. This combined assault from radiation and wind acts like a cosmic paddle, vigorously stirring the gas and adding another significant source of turbulent energy. Even the grand rotation of the galaxy itself may contribute. As the Milky Way spins, its differential rotation, where inner regions orbit faster than outer ones, can stretch and shear gas clouds, imparting a large-scale motion that might cascade down into smaller turbulent eddies. It's likely that all of these mechanisms work in concert, a symphony of violence where supernovae provide the percussive blasts, stellar feedback adds a constant rhythmic drive, and galactic shear sets the underlying tempo. However, identifying the sources is only half the battle. The other great mystery is how this turbulence dies down. Energy cannot simply disappear, it must be transferred and dissipated. This is the problem of dissipation, and it's a complex one. In a fluid like air, turbulence dissipates through viscosity, the friction between molecules that eventually converts motion into heat. But the interstellar medium is a near-perfect vacuum, far emptier than any we can create on Earth. The particles are so spread out that this molecular viscosity is practically zero. A turbulent eddy could, in theory, spin for millions of years without slowing down. But we don't see that. The turbulence we observe does dissipate, and relatively quickly. So how does it happen? The answer is believed to lie in magnetism. The interstellar medium is permeated by magnetic fields, and these fields are coupled to the ionized component of the gas. As turbulent motions try to move this gas, they must also drag the magnetic field lines with them, stretching and bending them. This creates magnetic tension, a force that resists the motion and effectively acts as a kind of magnetic viscosity, transferring energy from the large, chaotic motions down to smaller and smaller scales. At the very smallest scales, this energy is finally converted into heat through a process called magnetic reconnection, where tangled field lines snap and reorganize themselves, releasing their pent-up energy. It's an invisible, intricate process where the energy of a light-year-wide whirlpool is ultimately transformed into a faint warming of the gas through the subtle workings of magnetism. Understanding this cascade, from the largest drivers to the smallest dissipative scales, is one of the most computationally difficult problems in astrophysics, requiring simulations that can track these interactions across an enormous range of size and time. Unraveling this mystery is key to predicting the life cycle of galaxies, as the balance between turbulence's support and its decay ultimately dictates how a galaxy breathes, forming stars and evolving over billions of years. Yet for all the chaos stirred up by turbulence, the interstellar medium is also a place of astonishingly delicate and precise chemical craftsmanship. We've already encountered the widespread presence of large organic molecules like PAHs, but the chemical prowess of space goes far beyond that. Deep within the cold, dark hearts of molecular clouds, radio telescopes have detected a veritable menagerie of complex organic molecules. We're not just talking about simple carbon compounds, we're finding molecules that would look perfectly at home in a biochemistry lab on Earth. Significant quantities of ethyl alcohol, the very same alcohol found in alcoholic beverages, acetic acid, the primary component of vinegar, even simple sugars like glycoldehyde, a basic building block for more complex carbohydrates. And perhaps most tantalizing of all, precursors to amino acids, the fundamental components of proteins and life itself. Finding such sophisticated chemistry in an environment that is essentially a near-perfect vacuum and only a few degrees above absolute zero is utterly counterintuitive. It defies everything we know about how reactions work on Earth, where we rely on heat and pressure to bring molecules together. So how does the cold, empty void of space become such a prolific organic chemist? The answer lies on the surface of the most humble of cosmic objects, the interstellar dust grain. In the vast emptiness of a molecular cloud, a lone gas atom might drift for hundreds of years before it has a chance to collide with another atom. The probability of a three-body collision necessary for many complex reactions is virtually zero, but these microscopic dust grains act as tiny meeting halls, solving the problem of distance. When a wandering atom or a simple molecule like carbon monoxide bumps into a dust grain, weak intermolecular forces called van der Waals forces cause it to stick to the surface. It becomes adsorbed, held in place just long enough for another atom to land nearby. This process is known as surface-mediated chemistry, and it turns each minuscule speck of dust into a catalytic platform where the improbable becomes possible. The incredibly cold temperature, which seems like an obstacle, is actually an essential ingredient. It prevents the newly formed molecules from immediately vibrating themselves apart, granting them a fragile stability. Over millennia, these grains can become coated in a mantle of mixed ices, water, carbon monoxide, methane, and ammonia, creating a frozen matrix that is anything but inert. It is a silent, frozen laboratory, pre-processing the raw materials of the cosmos. But simply bringing atoms together on a cold surface isn't enough to explain the formation of truly complex bonds. For that, the system needs an energy source, a trigger to push reactions over the necessary energy barriers. This is where two unlikely allies come into play: cosmic rays and ultraviolet radiation. Despite being a destructive force, ultraviolet radiation from distant stars can penetrate the outer layers of molecular clouds. When a UV photon strikes a molecule trapped in an ice mantle on a dust grain, it can deposit just enough energy to break specific chemical bonds or create highly reactive radicals, which then scurry across the grain's surface to find new partners and form new, more complex molecules. It's a process called photolysis, effectively using light to do the work of heat. Even more effective are cosmic rays. These high-energy particles can tunnel deep into a cloud, and when they slam into a dust grain, they deposit a tremendous amount of localized energy, creating tiny, transient hotspots that can drive a cascade of chemical reactions in the icy mantle before it quickly refreezes. This combination of a cold, stable surface and sporadic bursts of energy is the secret recipe. It allows for a slow, methodical buildup of molecular complexity, one atomic addition at a time, creating molecules that would be instantly destroyed if they were free-floating in the gas phase. The implications of this discovery are staggering. It means that the fundamental organic chemistry that is a prerequisite for life is not unique to Earth. It is a universal process happening right now in the dark clouds that drift between the stars. The molecular clouds that give birth to stars are also chemical factories, and when a new star and its surrounding protoplanetary disk form, these complex organic molecules are already baked into the recipe. They become part of the comets, asteroids, and planetesimals that make up the new solar system. When those celestial bodies later bombard the surface of young planets like early Earth, they deliver this rich cargo of prebiotic material. The alcohol, the sugars, the amino acid precursors, all of it could have been raining down on our planet from the very beginning, providing a head start for the emergence of life. The chemistry of life, therefore, may not have started in a warm little pond on Earth, but in the deepest, coldest reaches of space on the surface of a speck of dust, activated by the radiation from a dying star light years away. This transforms our perspective of the cosmos from a largely inorganic void to a place that is actively, and seemingly inevitably, brewing the ingredients of biology. But as we map the swirling motions of gas and the grand rotation of entire galaxies, we are forced to confront a force even more mysterious and pervasive than the interstellar medium itself. For all the immense mass we can see the stars, the glowing nebulae, the dark molecular clouds, it is not enough. When astronomers measure how fast galaxies spin, they discover something astonishing. The visible matter, everything we can observe with our telescopes, simply does not have enough gravitational pull to hold these vast structures together. Stars on the outer edges of spiral galaxies are whipping around so fast that they should be flung off into intergalactic space like mud spinning off a tire. The fact that they aren't means only one thing: there must be far more mass in a galaxy than we can see. This missing mass, this invisible gravitational glue, is what we call dark matter. Dark matter is not simply a cloud of normal gas that's too faint to see. We know that because it doesn't absorb or emit any form of light or radiation we can detect. It is something else entirely, a substance that interacts with the universe seemingly through gravity alone. Its presence is felt, not seen. And while dark matter is not a component of the interstellar medium itself, its ghostly gravitational influence is the ultimate puppeteer, shaping the entire stage upon which the ISM performs. The majestic spiral arms of our galaxy, the vast halo that surrounds it, and even the overall distribution of the gas between stars are all sculpted by the dominant, unseen pull of dark matter. It creates the deep gravitational wells that guide the flow of interstellar gas, funneling it into the patterns we observe and setting the initial conditions for everything from the largest nebula to the smallest star-forming core. The influence of this dark scaffolding is particularly dramatic on the very largest scales of the interstellar medium. The rotation curve of a galaxy, a graph showing how the orbital speed of stars and gas changes with distance from the center, should, according to Newtonian physics, fall off sharply in the outer regions where visible matter becomes sparse. Instead, these curves remain flat, indicating that stars and gas are orbiting at high speeds far out in the galactic hinterlands, held in the grip of an enormous, invisible mass of dark matter that forms a spherical halo around the entire galaxy. This halo's gravity acts as a guiding hand, influencing how and where immense streams of gas can flow into the galaxy from intergalactic space, and how structures like the galactic fountain operate. It is the hidden architecture that determines the very shape and dynamics of the galactic ecosystem. Understanding the precise nature of this interaction is one of the most active fronts in astrophysics. Supercomputer simulations that model the evolution of the universe almost always begin with dark matter as the foundational element. Ordinary matter, the stuff of stars, planets, and us, is just along for the ride, falling into the gravitational potentials carved out by the dark matter. These simulations show that without dark matter's early gravitational pull, the slight density fluctuations in the infant universe would never have amplified enough to form the galaxies and galaxy clusters we see today. The interstellar medium, in all its complex phases, exists within the invisible contours of a dark matter skeleton. The distribution of the hot ionized medium, the filamentary structure of molecular clouds, and the very rate of star formation may all be subtly governed by the underlying distribution of this mysterious substance. And yet, for all its obvious gravitational influence, the true identity of dark matter remains arguably the greatest unsolved problem in all of physics. What is it made of? The leading candidate is a hypothetical class of particles known as WIMP, or weakly interacting massive particles. These would be exotic, heavy particles that rarely interact with normal matter except through gravity and perhaps the weak nuclear force. But despite decades of searching with incredibly sensitive detectors buried deep underground to shield them from cosmic rays, not a single definitive WIMP has been found. Other theories propose different candidates like actions, which are extremely light particles, or even primordial black holes formed in the universe's first moments. Each possibility leads to different predictions for how dark matter might be structured on small scales, which would in turn change how it influences the clumping and behavior of the interstellar gas within a galaxy. This profound ignorance means that while we can map dark matter's gravitational shadow, we are essentially blind to its microphysics. We don't know if dark matter particles can interact with each other in ways beyond gravity, or if they can be influenced by the very gas they control. This uncertainty creates a lingering question over all our models of the interstellar medium. Are we missing a key piece of the puzzle? Could unknown interactions between dark matter and ordinary matter be subtly influencing the temperature, the turbulence, or the collapse of gas clouds in ways we haven't yet imagined? The presence of dark matter is a fundamental truth of our universe, a silent partner in the cosmic dance of gas and dust, whose steps we can follow but whose nature we have yet to fully comprehend. If the interstellar medium is the canvas of the galaxy, then supernova remnants are the titanic brushes that splash it with energy, color, and newly forged elements. These expanding shells of debris are the primary agitators of the galactic ecosystem, the great engines of chaos that stir the gas, seed it with heavy atoms, and trigger new rounds of star birth. Yet for all their obvious power, the precise physics unfolding within their shock fronts remains a deeply complex and tantalizingly unresolved puzzle. The birth of a remnant is one of the most violent events in the universe. When a massive star exhausts its nuclear fuel, its core collapses catastrophically in less than a second, rebounding in an explosion that outshines its entire host galaxy. This detonation blasts the star's outer layers into space at speeds exceeding 30,000 kilometers per second, creating a rapidly expanding fireball of incandescent gas. This ejector plows into the surrounding interstellar medium like a cosmic snowplow, scooping up material and compressing it into a dense, bright shell. This shell is the supernova remnant, and it is within this thin, incredibly energetic boundary layer that the universe's most fascinating physics takes place. The most critical process happening at this shock front is particle acceleration, the very mechanism we believe is responsible for creating cosmic rays. As the supersonic shock wave tears through space, it generates a maelstrom of tangled magnetic fields. Charged particles, primarily protons and electrons from the surrounding gas, get caught in this magnetic turbulence. They don't simply cross the shock once, they bounce back and forth across it countless times, trapped as if in a chaotic magnetic pinball machine. With each crossing, they gain a tremendous boost of energy from the moving magnetic fields. This process, known as Fermi acceleration, can take a languid proton from the interstellar medium and accelerate it to nearly the speed of light, transforming it into a high-energy cosmic ray. These particles are then ejected into the galaxy, where they will travel for millions of years, influencing chemistry and posing risks to any potential life they encounter. Simultaneously, the shock wave performs a feat of immense violence on the gas it encounters. The interstellar medium ahead of the shock might be a calm, cold cloud of hydrogen. But when the shock front hits, it doesn't gently push this gas aside. It slams into it, compressing it by factors of hundreds or even thousands, and heating it through direct compression to temperatures exceeding 10 million degrees. At these temperatures, the gas is completely ionized, stripped down to its constituent atomic nuclei and free electrons, creating a searing plasma that glows intensely in X-rays. This is how supernova remnants become the primary source for the hot ionized phase of the interstellar medium, effectively cooking vast volumes of space and preventing them from immediately collapsing back into stars. Perhaps the remnant's most profound role, however, is that of galactic alchemist. The star that exploded didn't just fuse hydrogen into helium during its life. In its final days, and in the unimaginable conditions of the supernova explosion itself, it forged the heavier elements that are the building blocks of planets and life. The intense heat and neutron flux created atomic nuclei like oxygen, silicon, sulfur, and iron elements that simply did not exist in the primordial universe. The expanding remnant acts as a delivery vehicle, taking this freshly synthesized material and scattering it far and wide into the galactic environment. It is literally pollution on a cosmic scale, but it is this pollution that enriches the galaxy, ensuring that future generations of stars form from gas that already contains the necessary ingredients for rocky planets. The iron in our blood and the calcium in our bones were once blasted across space in the remnant of a long-dead star. The greatest mysteries today revolve around how these remnants interact with the complex surroundings they expand into. The textbook image of a perfect spherical remnant is almost never what we see. Instead, telescopes reveal fantastically intricate structures, lopsided shells, twisting tendrils, and chaotic swirls. This is because the ejector slams into an interstellar medium that is itself wildly irregular, filled with clumps of dense molecular clouds, bubbles of hot gas, and tunnels carved by previous stellar winds. The shock wave does not propagate uniformly. It may slam into a dense cloud and slow almost to a crawl while racing through a neighboring region of low-density gas. This can fragment the shell, create powerful instabilities, and lead to incredibly complex mixing of the hot ejector and the cold cloud material. Understanding this interaction is crucial because it dictates the ultimate fate of the remnant's energy and its enriched cargo. Does the energy get efficiently deposited into stirring the interstellar medium, or is it radiated away too quickly? How efficiently are the heavy elements mixed into the surrounding gas? Current computer models struggle to simulate this chaos across the vast range of scales involved, from the parsec-sized cloud down to the microphysics of the shock itself. Each new high-resolution image from telescopes like Chandra or James Webb reveals more complexity, showing us that the final act of a star's life is not a simple blast, but a prolonged and intricate dialogue with the galaxy it helped to shape. While the ultraviolet fury of a massive star is indeed the engine that lights up vast clouds of ionized hydrogen, the sheer complexity of how this energy carves out and shapes these celestial bubbles is a world of hidden physics. An H2 region is not simply a uniform, glowing fog. It is a dynamic and constantly evolving battlefield where light fights a relentless war against gravity and matter. The process begins with an O or B-type star, a behemoth that burns hot and fast, flooding its surroundings with a torrent of high-energy UV photons. These photons are so energetic that when they strike a neutral hydrogen atom, they don't just excite it, they violently strip away its electron, ionizing it in a flash. This creates a growing sphere of influence around the star, a zone where the gas is heated to a scorching 10,000 degrees Kelvin, and begins to glow with the characteristic red light of recaptured electrons. The boundary of this sphere is where the true mystery unfolds, the ionization front. This is not a static wall, but a thin, incredibly precise region where the star's radiation field meets the cold, neutral gas of the surrounding molecular cloud. The front propagates outward at supersonic speeds, but its progress is dictated by a delicate balance. The rate at which it expands depends on the density of the gas it's encountering and the unyielding output of ionizing photons from the central star. Think of it like a blowtorch hitting a block of ice. The torch's power is constant, but the ice's density and structure determine how quickly it melts and what intricate shapes are formed. This creates a stunning variety of structures, from the vast, relatively smooth expanses of an H2 region to the intricate elephant trunk pillars of creation, where dense knots of gas were able to temporarily shield themselves from the advancing front, creating shadowy sculptures that are themselves the birthplaces of the next generation of stars. Perhaps the most significant challenge in modeling these regions is the profound influence of the very dust that is mixed within the gas. Those microscopic grains are not passive spectators. They are active competitors for the star's energetic photons. A significant portion of the ultraviolet radiation is absorbed by dust grains instead of hydrogen atoms, heating the dust and causing it to radiate in the infrared. This dust absorption effectively steals energy that would otherwise be used to ionize more hydrogen, putting a brake on the expansion of the ionization front and altering the predicted size and temperature of the nebula. The dust also becomes a crucial coolant, as its infrared emission allows energy to escape the system, further complicating the thermal balance of the entire region. This means that to accurately model an H2 region, astrophysicists must account for a complex three-way interaction between radiation, ionized gas, and solid dust particles, all of which are constantly influencing each other in a feedback loop that is notoriously difficult to simulate. The final shape and fate of these nebulae are also a direct record of the star's own life story and the environment it was born into. A star born in the relative isolation of a low-density cloud will create a vast spherical bubble known as a Sturmgren sphere, a nearly perfect volume of ionized gas. But a star born in the dense, chaotic heart of a giant molecular cloud will create a far more constrained and irregular nebula, its ionizing radiation desperately fighting to clear out a cavity within the stubborn, crowded gas. Furthermore, as the star ages, its output of UV photons will change, and powerful stellar winds will begin to blow, adding another layer of complexity. These winds can physically push material away, carving out cavities and creating shock waves that compress surrounding gas into shells and filaments. The beautiful, billowing structures we see in images of the Orion Nebula or the Tarantula Nebula are not just sculptures of light. They are the frozen fingerprints of this intricate and ongoing dance between radiation, wind, and gravity, a cosmic struggle that we are only beginning to fully comprehend. But these spectacular stellar factories and the vast structures of the interstellar medium do not exist in isolation. They are part of a grander cycle of inflow and outflow that connects our galaxy to the space beyond. Drifting toward the Milky Way from the immense darkness between galaxies are enigmatic structures known as high-velocity clouds. These are not small wisps of gas. They are colossal rivers of mostly neutral hydrogen, some containing enough mass to form millions of stars, and they are plummeting toward our galactic disk at speeds that defy simple explanation. Their motion is so rapid and directed that it cannot be reconciled with the orderly rotation of the Milky Way itself. They are interlopers falling in from the void, and their origin story is a key piece in the puzzle of how galaxies gather their material and grow over time. The primary mystery lies in their incredible velocity and their location. These clouds are observed high above the plane of the galaxy in the galactic halo, and their movement is almost purely radial, aimed directly inward. This distinguishes them from the material that is simply orbiting within the disk. So where is this gas coming from? One compelling theory suggests these clouds are the long-predicted cold accretion flows from the cosmic web. According to our models of structure formation, galaxies should be continually fed by delicate filaments of pristine, cold gas that stream in from intergalactic space, providing the fresh fuel needed for sustained star formation. High-velocity clouds could be the actual, observable manifestation of this process, the rivers that are feeding our galaxy, delivering hydrogen that has never been cycled through a previous generation of stars. This would make them primordial, a living fossil from the early universe that is still trickling in billions of years later. However, not all this infalling gas is pristine. Observations reveal a complicating and fascinating detail. The chemical makeup of these clouds is not uniform. Some show a severe deficiency in heavy elements, supporting the idea that they are indeed virgin material from the intergalactic medium. But others possess a significant metallicity. They are enriched with elements like oxygen, silicon, and iron that could only have been forged in the furnaces of massive stars and scattered by supernovae. This points to a second, equally dramatic origin story. These clouds could be the returning tidal debris from ancient galactic collisions. Our Milky Way has a history of cannibalizing smaller dwarf galaxies, and during these violent encounters, vast streams of gas can be ripped away from the victim and flung far out into the halo. This gas would later turn around, and begin a long fall back toward the Milky Way, now appearing as a high-velocity cloud that carries the chemical signature of its stellar origins. This connects directly to a third possibility, the galactic fountain model we explored earlier. In this cyclical process, supernova explosions within the disk can blow bubbles of hot gas high up into the halo. This gas then cools, condenses into clouds, and falls back down as a high-velocity rain. In this scenario, the clouds aren't external at all. They are our own galaxy's material, launched on a monumental journey only to return home. The challenge for astronomers is untangling these different histories. A single cloud falling toward us could be a first-time visitor from the intergalactic void, the scattered remains of a devoured galaxy, or a returning parcel of our own recycled material. Determining which is which requires meticulous detective work, analyzing not just a cloud's speed and direction, but its detailed chemical composition to read the story of its past. The fate of this material once it arrives is just as crucial as its origin. When these massive clouds finally collide with the gaseous disk of the Milky Way, the impact is not gentle. They slam into the thinner interstellar medium at supersonic speeds, creating powerful shock waves that compress the gas they encounter. This compression can be the trigger for new star formation, directly linking the infall of gas from the halo to the birth of new stellar generations. This ongoing accretion is essential for the galaxy's future. Without this fresh inflow of fuel, the Milky Way would eventually consume all its available gas and star formation would sputter out. The silent, relentless rain of high-velocity clouds is what keeps our galaxy alive and vibrant, ensuring that new stars will continue to light up the spiral arms for billions of years to come. They are a dramatic reminder that our galaxy is not a closed system. It is an open, breathing entity, constantly interacting with and drawing sustenance from the vast cosmic ocean that surrounds it. Now we arrive at a mystery that takes us right back to the very beginning, connecting the vast interstellar medium to the first few minutes of the universe itself. It's known as the cosmological lithium problem, and it's a classic case of the universe failing to follow its own recipe. In the hot, dense aftermath of the Big Bang, a process known as Big Bang nucleosynthesis forged the universe's first atomic nuclei, vast amounts of hydrogen and helium, and trace quantities of two heavier elements, deuterium and lithium. For the most part, our calculations of this primordial cooking match the observed abundances of these elements almost perfectly, a stunning confirmation of our standard model of cosmology. But there is one glaring exception. When we look out at the oldest stars in the halo of our galaxy, which are made from nearly pristine gas that has undergone little recycling, the amount of lithium-7 we find is only about 1/3 of what the theories predict. Somehow, across billions of years, a significant portion of the universe's original lithium has gone missing. This isn't a small accounting error. It's a fundamental discrepancy that forces us to question our understanding of both the infant universe and the galactic processes that have been at work ever since. So where did it go? The lithium couldn't just disappear. The leading suspicion is that it is being destroyed somewhere along the line, and the interstellar medium is a prime suspect in this cosmic mystery. Lithium is a fragile and highly reactive element. It doesn't take much to break its nucleus apart or lock it away in chemical compounds. The journey from its creation in the Big Bang to its incorporation into a star whose atmosphere we can study is a long and perilous one, filled with opportunities for it to be lost. One compelling theory points the finger at those ubiquitous cosmic dust grains. As lithium atoms drift through the interstellar medium, they can stick to the surfaces of these microscopic particles. Once there, they become susceptible to a process called spallation, where they are bombarded by high-energy cosmic rays. These impacts could potentially shatter the fragile lithium nuclei, effectively erasing them from the inventory. Alternatively, the lithium could be locked away in stable chemical compounds on the grain's surface, forming lithium hydride or other molecules that are difficult for astronomers to detect with our current methods. In this scenario, the dust grains act as a kind of cosmic sponge, soaking up the primordial lithium and hiding it from view, effectively filtering it out of the gas phase that we typically observe. But the interstellar medium might not be working alone. Stars themselves could be accomplices in this disappearance. The oldest stars we use to measure the primordial lithium abundance are low-mass, long-lived stars. Their outer atmospheres are relatively cool, which is why we can detect lithium there at all. In hotter stars, it would be quickly destroyed. However, models of stellar physics suggest that even in these cooler stars, processes like diffusion could be slowly dragging lithium atoms from the surface down into the hotter interior, where temperatures are high enough to burn them up in nuclear reactions. If this is happening universally, then every ancient star we look at would show a depleted lithium level, not because it wasn't there to begin with, but because the stars themselves have been destroying their own supply over billions of years. This would mean we are getting a false reading of the true primordial abundance. Resolving this mystery is about much more than finding a missing element. It strikes at the heart of our confidence in the Big Bang theory itself. The predicted abundances of hydrogen, helium, and deuterium are such a precise match to observations that they are considered a pillar of modern cosmology. The lithium problem is the one loose thread that, if pulled, could potentially unravel our understanding of the universe's first few minutes. Did we get the nuclear reaction rate slightly wrong in our models of the early universe? Is there some unknown particle or energy field that was present and influenced those first nuclear reactions? Or is the solution to be found in the complex astrophysics that has occurred in the 13 billion years since, within the turbulent and dusty confines of the interstellar medium and the stars that form within it. Each possibility leads us down a different path of discovery, reminding us that sometimes the biggest secrets of the cosmos are hidden in the smallest of details. While we often picture our solar system voyaging through a typical patch of the interstellar medium, the reality is far more specific and strangely cozy. We are actually traveling through the interior of a vast, cavernous structure known as the local bubble. This isn't a void in the true sense, but a region of space shaped by immense violence and filled with an incredibly thin, scorching hot plasma. Imagine a cosmic Swiss cheese where the holes are bubbles blown by stellar explosions, and our sun just happens to be passing through one of the largest and most fascinating of these cavities. This is our local galactic neighborhood, a celestial hot air balloon roughly 300 light-years across, and its origin story is a detective case written in supernova shock waves. The prevailing theory for the bubble's creation is as dramatic as it is ancient. Astronomers believe that sometime between 10 and 20 million years ago, a string of massive stars, likely all members of a single stellar association that has since dispersed, reached the end of their lives in a relative cosmic blink of an eye. One after another, these titans exploded as supernova. Their cataclysmic final acts did not happen in isolation. Their collective shock waves expanded outward, merging into a single, gargantuan front that acted like a cosmic plow. This powerful wave swept up the colder, denser gas and dust of the surrounding interstellar medium, pushing it outward and piling it up into a dense, complex shell that defines the bubble's surface. Meanwhile, the interior was left filled with the supernova ejecta itself, a tenuous but seething soup of million-degree gas, ionized and glowing faintly in X-rays. The mysteries surrounding this structure are not about its existence, but its precise biography. We are still trying to determine the exact number of stars that contributed to this celestial excavation project. Was it a dozen titans or more? Pinpointing the timing is equally challenging. Did these explosions occur in a rapid-fire sequence over just a few million years, or were they more spread out, allowing earlier shock waves to begin fading before being re-energized by the next blast? Perhaps the most intriguing question is the location of their epicenters. Using advanced star motion data from telescopes like Gaia, astronomers are now engaged in a form of galactic rewinding, tracing the paths of nearby stars and the surviving remnants of supernova backwards in time to see which ones were positioned perfectly to have their explosions shape our local space. Adding to the complexity is the bubble's surface itself. This is not a smooth, perfect sphere like a soap bubble. It is a rugged, multifaceted landscape of accumulated material. Where the expanding shock wave encountered pre-existing dense clouds, it slowed down, leaving behind towering pillars and dense knots of gas. In other areas where the interstellar medium was thinner, the wave raced ahead, creating thinner sections of the shell. This results in a surface that looks more like a mountain range than a wall, with famous nebulae like the Orion Molecular Cloud Complex potentially being part of this colossal boundary. Mapping this intricate topography in 3 dimensions is an ongoing effort, requiring us to combine data from many different telescopes sensitive to various wavelengths of light, each revealing a different layer of the structure. This local environment has profound implications for our own place in the cosmos. The fact that we reside inside this bubble has directly shaped our view of the galaxy. Because the interior is so empty of obscuring dust, we have a relatively clear sightline out to the bubble's walls and beyond in several directions, offering us a window into the wider interstellar medium that would otherwise be blocked. It also affects the local environment of our solar system. The density of material, our heliosphere, the protective magnetic bubble generated by the sun must navigate, is significantly lower here, which in turn influences the number of cosmic rays that can reach our inner solar system. We are living inside a celestial landmark, a temporary haven carved out by long-dead stars, whose precise history we are only now beginning to read. While our sun may seem like the dominant force in our celestial neighborhood, it is in constant motion, sailing through the galaxy and navigating the subtle currents of the local interstellar medium. This journey creates a unique and dynamic boundary where the solar system meets the galaxy, a region governed by the flow of the solar wind and the pressure of the interstellar gas. It is here, in this contested frontier, that we encounter a fascinating class of particles known as interstellar pickup ions, which serve as minuscule messengers from the vast expanse beyond our solar system. The story of a pickup ion begins with a lonely atom of hydrogen or helium drifting in the near-perfect vacuum of the interstellar medium. For eons, this atom has been part of the local cloud of gas through which our sun is moving. Eventually, the tenuous pull of the sun's gravity draws it inward, across the invisible boundary of the heliosphere and into the solar system. As it journeys closer to the sun, it is bombarded by intense solar ultraviolet radiation. This radiation strips the atom of its electron in a process called photoionization, transforming it from a neutral particle into a positively charged ion. Suddenly, this new ion finds itself in the path of the supersonic solar wind, a relentless stream of charged particles flowing outward from the sun at over 1,000,000 miles per hour. The magnetic field embedded within this solar wind immediately snags the freshly created ion, picking it up and accelerating it away from the sun. This entire transformation from a slow-moving interstellar neutral to a high-energy pickup ion happens in an instant. Detecting these particles is a monumental scientific achievement. Spacecraft like NASA Voyager probes and the Advanced Composition Explorer have instruments specifically designed to identify them. The key to their detection lies in their unique velocity signature. Unlike the solar wind particles, which all stream radially outward from the sun at roughly the same high speed, pickup ions have an additional, distinct motion imparted by the sun's movement through the galaxy. This gives them a telltale spread in velocity that acts like a fingerprint, allowing scientists to single them out from the background of normal solar wind. By carefully analyzing the composition and quantity of these ions, we are essentially performing a direct chemical analysis of the local interstellar cloud, sampling its elemental and isotopic makeup without ever having to leave the solar system. It is as if the solar wind is doing our fieldwork for us, collecting samples from the galactic environment and delivering them to our detectors. The behavior of these pickup ions is inextricably linked to the structure of the heliosphere itself, the giant magnetic bubble that the solar wind inflates in the interstellar medium. The size and shape of this protective bubble are not fixed. They are determined by a delicate balance of pressures. The outward pressure from the solar wind pushes against the inward pressure of the interstellar gas and the galactic magnetic field. The influx of interstellar neutrals plays a critical role in this balance. As these neutrals enter the heliosphere and become ionized, they add mass and energy to the solar wind, altering its properties and affecting how far it can push out into the galaxy. This interaction makes the entire heliospheric boundary a dynamic and complex interface, one that is constantly shifting in response to changes in both the solar wind and the local interstellar environment. This brings us to one of the most tantalizing mysteries revealed by the Voyager missions, the unexpected nature of the heliosphere's boundaries. As the Voyager probes crossed first the termination shock, where the solar wind slows from supersonic to subsonic speeds, and then finally the heliopause, the true boundary between the solar wind and the interstellar plasma, the data they sent back was surprising. The inferred shape and pressure of the local interstellar medium did not perfectly match our pre-flight models. The magnetic field direction just outside the heliopause was different than anticipated, and the interaction region appeared more complex and structured. The presence and influence of pickup ions are a key factor that earlier models may have underestimated. suggesting that their contribution to the pressure and thermodynamics of the outer heliosphere is more significant than we once thought. Understanding this cosmic balancing act is not merely an academic exercise. It has profound implications for our place in the galaxy. The heliosphere acts as a crucial shield, deflecting a substantial portion of the galactic cosmic rays that would otherwise bombard the inner solar system. These high-energy particles can damage spacecraft electronics and pose a potential radiation hazard to future interplanetary travelers. The efficiency of this shielding depends directly on the heliosphere's size and integrity, which are in turn shaped by the very interstellar pickup ions we are studying. By deciphering the physics of this boundary, we learn not only about the galaxy's influence on our solar system, but also about the fundamental processes that define the habitable zones around other stars, where similar astrospheres must protect their own planetary systems. And now we turn to a mystery of cosmic scarcity, a case of the missing elements that reveals just how much the interstellar medium can vary from one neighborhood to the next. If you were to take a sample of the Sun's atmosphere, or even the average composition of our entire solar system, you would find a predictable mix of elements: a certain amount of hydrogen, a dash of helium, and trace quantities of everything else, from carbon and oxygen to iron and titanium. This is our cosmic baseline, but when astronomers point their spectroscopes at distant clouds of interstellar gas, they find something strange. Certain elements, particularly metals like iron, calcium, and titanium, are far less abundant in the gas phase than they should be. They haven't vanished, they've simply vanished from view, having been removed from the gaseous state and locked away elsewhere. This phenomenon is known as depletion, and the pattern of which elements are missing and by how much tells a complex story of dust's life cycle. The primary suspect in this cosmic heist is once again interstellar dust. The logic is straightforward. In the cold depths of space, atoms that are prone to forming solid compounds will naturally condense onto any available surface, especially pre-existing dust grains. Think of it like frost forming on a window pane on a cold morning. The water vapor in the air is depleted as it freezes onto the glass. In space, elements with high condensation temperatures, like iron, silicon, and magnesium, are the first to freeze out of the gaseous soup and stick to dust grains. This is why we find silicate grains rich in silicon and magnesium, and carbonaceous grains which can lock away other metals. The grains act as cosmic sponges, soaking up these specific elements and effectively filtering them out of the gas we can observe with our telescopes. But here's where the mystery deepens. This depletion isn't a universal constant. It varies dramatically from one interstellar cloud to another. In some regions, like the diffuse clouds that let through plenty of starlight, the depletion of certain elements can be extreme. In these environments, up to 99.99% of an element like iron might be missing from the gas, almost certainly locked tightly within the protective bulk of dust grains. Yet in other regions, particularly denser molecular clouds or areas recently scoured by a supernova shock wave, the same elements might be far more present in the gas phase. This tells us that depletion is not a static condition but a dynamic process, a snapshot of a constant tug of war between creation and destruction. The varying levels of depletion act as a powerful diagnostic tool, a kind of chemical fingerprint that reveals a cloud's history and environment. A cloud showing severe depletion of refractory elements like iron and titanium is likely to be a mature, quiescent region. It has existed long enough and in a calm enough state for its dust grains to have efficiently vacuumed up nearly all the available metals from the gas, growing thick icy mantles in the process. Conversely, a cloud showing less depletion is probably a younger or more violent environment. Perhaps it has recently been blasted by a shock wave from a nearby supernova, an event so violent it can vaporize dust grains, shattering them back into their atomic components and returning those depleted elements to the gas in a process called sputtering. Or it could be a region where fierce ultraviolet radiation from hot stars is actively photoevaporating the icy mantles off grains, briefly re-releasing some of their trapped inventory. This means the depletion pattern we observe is a record of a cloud's past trauma and tranquility. It tells us about the shock waves it has endured, the strength of the radiation fields it has been exposed to, and its overall age and stability. By carefully measuring the depletion levels of dozens of different elements along a single line of sight, astronomers can essentially perform an archaeological dig through the interstellar medium, uncovering layers of history written in the subtle absences of specific elements. It is a profound reminder that the emptiness of space is not uniform. It is a tapestry of different environments, each with its own unique chemical story, its own balance of creation and destruction, and its own record of the epic cycles that continuously reshape the galaxy. We've seen how dust grains act as cosmic sponges and chemical factories, but there's another layer to their behavior that profoundly shapes their role in the galaxy: electric charge. Far from being neutral bystanders, these microscopic particles are almost always electrically charged, transforming them into active players in the physics of the interstellar medium. This charge doesn't come from a wall socket. It's the result of a constant, silent bombardment from the universe itself. In regions bathed in starlight, high-energy ultraviolet photons strike a dust grain and can knock electrons loose from its surface in a process called photoemission. This leaves the grain with a net positive charge, as it has lost negatively charged particles. Conversely, in darker, cooler clouds where UV light is scarce, the grains act like traps, capturing free-flying electrons from the surrounding gas and thus building up a negative charge. The equilibrium charge of any given grain at any moment is a delicate balance between these competing processes, a tiny testament to its local environment. This acquired charge might seem like a minor detail, but it fundamentally changes how dust interacts with everything around it. For one, it makes the grains exquisitely sensitive to magnetic fields. We've already discussed how the galaxy is laced with a pervasive magnetic field, but neutral particles are completely oblivious to it. A charged dust grain, however, is not. It becomes coupled to the field, its motion dictated by the invisible lines of force. In a practical sense, this means magnetic fields can effectively trap and organize charged dust, guiding it to form specific structures within a cloud or even helping to align the grains, which is crucial for creating the polarized starlight we use to map those very fields. The charge also dictates how the grains interact with each other. While neutral grains might stick together upon collision due to weak van der Waals forces, charged grains will electrically repel or attract each other. This electrostatic interaction can either inhibit or encourage their growth, directly influencing the early stages of planet formation where dust must clump together to form larger bodies. Perhaps the most significant consequence lies in how charged dust influences the overall behavior of the gas in a cloud. The interstellar medium is a plasma, a soup of ionized gas where electrons and ions move independently. When dust grains are present and charged, they become the dominant players in this electrical ecosystem. Because they are so much more massive than electrons or protons, they act as a kind of anchor, slowing down the motions of the lighter charged particles and dramatically increasing the electrical resistivity of the entire cloud. This might sound technical, but it has a staggering effect on star formation. Magnetic fields are supported by the movement of charged particles, and this high resistivity allows the magnetic field to diffuse through the cloud more easily, effectively slipping through the gas rather than being dragged along with it. This process, called ambipolar diffusion, is thought to be critical for allowing dense cores to collapse under gravity despite the supporting pressure of the magnetic field. In essence, the humble charged dust grain, by changing the electrical properties of its environment, acts as a silent midwife to the birth of new stars. The distribution of these charges is not uniform, creating a complex and nuanced problem for astrophysicists. A grain's charge depends critically on its size and composition. A larger grain has more surface area to absorb photons or electrons, but it also has a greater capacity to hold charge. The precise way charge builds up on an irregularly shaped, microscopic piece of carbon or silicate is fiendishly difficult to model. Furthermore, the environment is in constant flux. A passing shock wave or a burst of radiation from a nearby hot star can dramatically alter the charging rates for every grain in a region, shifting the entire electrostatic landscape in an instant. This means that to truly understand the dynamics of an interstellar cloud, how it collapses, how it fragments, how it evolves, we cannot treat it as a simple fluid of gas and neutral dust. We must view it as a complex electromagnetic plasma where tiny, charged dust grains hold a surprising amount of influence over the grandest cosmic processes. And just when we think we understand the chaotic journey of cosmic rays, their behavior reveals another layer of intricacy, a subtle clue written not in their immense power, but in their delicate distribution across the sky. According to our fundamental understanding, the path of a charged cosmic ray should be utterly scrambled by the galaxy's magnetic field. As these particles spiral around the invisible lines of force, their trajectories become so tangled that by the time they reach Earth, they should appear to be arriving from every direction equally, forming a perfectly smooth and uniform glow of high-energy particles. This expected isotropy is a direct consequence of the magnetic chaos they endure during their multi-million-year journeys. Yet, when scientists built detectors sensitive enough to map the cosmic ray sky with incredible precision, they discovered this was not the case. There is a pattern, an incredibly faint but very real anisotropy. The cosmic ray drizzle is not perfectly even. It has ripples, a slight overabundance coming from some directions and a slight deficit from others. It's as if we're standing in the middle of a chaotic, windy storm, but can somehow detect a faint, consistent breeze blowing from one specific corner of the sky. This anisotropy is minuscule, a variation of just about 1 part in 10,000, but its very existence is a monumental puzzle. It should have been completely erased by the magnetic maze of the interstellar medium. The fact that it persists means that the scrambling is not perfect, and that opens a door to understanding both the ray's origins and the nature of the magnetic fields they travel through. The leading explanation points to our local cosmic environment. The thinking is that we are not looking at the imprint of distant, powerful accelerators like supernova remnants in the far reaches of the galaxy. Instead, this faint directional signal is likely generated much closer to home, within our local interstellar neighborhood, perhaps within the last 1,000 light-years or so. If a source of cosmic rays is relatively nearby, the particles simply haven't had enough time or distance for their paths to be completely randomized by the magnetic fields. Their arrival directions could still retain a memory, a faint echo of their point of origin, like finding a handful of leaves in your garden that all seem to come from the same tree just over the fence. This immediately suggests a fascinating candidate: the local bubble, that vast cavity of hot, thin gas we reside in, which was carved out by a series of ancient supernovae. The shock waves from those explosions would have been perfect particle accelerators, and the cosmic rays they produced could still be echoing within this cavity, their paths influenced by the bubble's unique magnetic structure and its boundaries. Alternatively, the anisotropy might not be pointing directly to a source at all, but acting as a probe of the local magnetic field itself. The slight directional preference we see could be caused by the specific way cosmic rays diffuse along the magnetic field lines that happen to thread our immediate region of space. The local interstellar magnetic field might have a particular large-scale order or a grain to it, a prevailing direction that guides the particles just enough to create a detectable bias in their flow toward us. In this view, the anisotropy is less a signpost and more a weather vane, showing us the direction of the local magnetic current. Unraveling this mystery requires an extraordinary global effort, as no single detector can see the entire cosmic ray sky at once. Because cosmic rays are charged, their paths are bent by Earth's own magnetic field, distorting the incoming signal. To correct for this and piece together a true map of the anisotropy, scientists must combine data from a network of observatories spread across both hemispheres of the globe, from the Ice Cube Neutrino Observatory at the South Pole to the Telescope Array in Utah. These facilities work in concert to triangulate the cosmic ray sky, slowly building up a statistical picture of these tiny fluctuations. Each new data point adds to a map that is not of light, but of the relentless rain of atomic nuclei, a map that is slowly revealing the hidden structure of both the magnetic fields in our galactic backyard and the nearby engines that continue to fire these incredible projectiles through the void. Deep within the colossal, shadowy forms of molecular clouds, hidden from the light of stars, lie their ultimate secrets, the prestellar cores. These are the coldest, densest places in the entire galaxy, regions of such profound darkness and stillness that they represent the final moments before a star is born. To find them, astronomers cannot look for light. They must instead search for its absence or for the faintest whisper of cold. In telescope images, they appear as black smudges silhouetted against brighter nebula backgrounds, not because they emit darkness, but because their thick veils of dust and gas are so efficient at absorbing the background starlight. Alternatively, in the submillimeter and radio parts of the spectrum, these frigid cores themselves become faintly visible, glowing not with heat but with the minuscule amounts of energy they radiate as they cool, just a few degrees above absolute zero. They are the cradles of creation, the isolated wombs where gravity prepares to ignite a new sun, and the initial conditions locked within them hold the answers to some of the most fundamental questions in astronomy. The central mystery is one of pure potential. When we observe one of these cores, we are looking at a system on the very brink of collapse, a reservoir of gas and dust that has almost but not quite overcome all the forces supporting it. The precise arrangement of matter and motion inside this core in these final moments is what will dictate everything about the star or stars that form within it. Yet, peering into this opaque environment is like trying to predict the detailed structure of an oak tree by only looking at the acorn. Our current observations give us a blurry picture. We can measure a core's total mass, its rough size, and its average density, but we struggle to see the intricate internal structure. Is the density uniform, or are there already tiny, invisible knots of even denser material beginning to form deep inside? How is the gas moving? Is the entire core slowly rotating as a single object, or is it filled with complex, turbulent eddies? These initial conditions are the master blueprint for star formation, and we are still trying to decipher the architectural language. This leads directly to the puzzle of fragmentation, the process that determines whether a core becomes a single, solitary star like our Sun, or shatters into a litter of stellar siblings. Imagine a vast, slowly collapsing sphere of gas. As it shrinks under its own weight, it does not necessarily do so smoothly. Any slight irregularity in its density, any small swirl in its motion, can be amplified by gravity. A tiny, random clump that is slightly denser than its surroundings will exert a slightly stronger gravitational pull, drawing in more material and growing even denser, faster than the rest of the core. This can cause the single large core to break apart into several smaller, collapsing fragments, each destined to become its own star. This is the likely origin of most star clusters. But what tips the balance? The key seems to lie in the competition between gravity's tendency to create chaos and the magnetic fields and gas pressure that fight to maintain order. Supercomputer simulations show that the strength of the internal magnetic field is a crucial governor. A strong magnetic field can suppress fragmentation, effectively stiffening the core and forcing it to collapse more or less as a single unit to form one massive star. A weaker field allows gravity to run wild, splintering the core into many smaller pieces that will become a whole family of lower mass stars. Yet magnetism is not the only actor in this play. The core's initial temperature and its level of internal turbulence are equally critical players. A warmer core has higher thermal pressure pushing outward, resisting collapse and allowing more time for gravitational instabilities to grow and fragment the cloud. A colder core, conversely, can collapse more quickly and monolithically. Turbulence adds another layer of beautiful complexity. It can provide support against collapse on large scales, but on smaller scales, it can actually seed the very density fluctuations that lead to fragmentation. It's a paradoxical force, both hindering and helping the process of star birth. The interplay of all these factors, mass, magnetism, temperature, and turbulence, creates a vast parameter space of possibilities, and astronomers are only now, through increasingly sophisticated numerical models, beginning to map out which combinations of initial conditions lead to which stellar outcomes. Ultimately, understanding these dense cores is about understanding our own origins. Our solar system, with its single star and orderly planets, is the product of a core that avoided significant fragmentation. Was this due to a particularly strong magnetic field, or was it simply a very quiet, tranquil cloud that collapsed without much internal turmoil? By studying the diverse population of cores within our galaxy, some destined to be singles, others to be clusters, we are piecing together the odds that led to our existence. Each dark core is a frozen moment, a snapshot of a universe poised on the edge of creation, and by learning to read their faint signals, we are uncovering the subtle physics that decides between a lone star shining in the void and a brilliant cluster lighting up the galactic night. This grand cycle of the interstellar medium, from pristine gas to stellar fuel and back to enriched waste, is the very heartbeat of a galaxy. It's a story that connects the microscopic to the cosmic, where the fate of 100 billion stars is governed by the subtle physics unfolding within vast, dark clouds. The profound mystery we now face is understanding how these local, small-scale processes the churn of turbulence in a single nebula, the strength of a magnetic field around a prestellar core, the chemical reactions on a dust grain collectively add up to dictate the grand, sweeping narrative of galactic evolution. How does the chaos of a supernova blast in one spiral arm influence the rate at which stars are born light years away, and ultimately determine whether a galaxy blazes with starbirth or fades into a quiet, reddened retirement? The engine of this evolution is the star formation rate, and it is anything but constant. We observe some galaxies, known as starburst galaxies, where star formation is a veritable frenzy, consuming the interstellar gas reservoir at a ferocious pace that cannot be sustained for more than a fraction of the galaxy's life. In contrast, other galaxies like our own Milky Way maintain a more measured, steady pace of star birth, while still others, particularly large elliptical galaxies, have become virtual deserts, their star formation having effectively ceased eons ago. This disparity in galactic lifestyles isn't just a matter of how much gas a galaxy started with. It's a direct consequence of how efficiently the interstellar medium within it cycles and regulates itself. The galaxy's ultimate fate, whether it remains a vibrant blue spiral or evolves into a red and dead elliptical, is written in the complex interplay of forces within its gaseous clouds. So what are the governing mechanisms? How do the small-scale rules enforce large-scale order? It begins with feedback, a self-regulating loop where star formation itself eventually acts to suppress further star formation. The most massive stars are tremendously powerful but tragically short-lived. Within a few million years of their birth, they flood their natal cloud with intense ultraviolet radiation and powerful stellar winds, which heat and ionize the surrounding gas, dramatically increasing its pressure and halting further gravitational collapse. This effectively shuts down star formation in their immediate vicinity. Then, in a final spectacular act, they explode as supernova. These explosions do more than just enrich the medium with heavy elements. Their blast waves violently churn the interstellar gas, stirring it into a froth of turbulence that can both compress some regions to trigger new star birth while simultaneously dispersing others, preventing them from collapsing. This creates a system of self-regulation. Too much star formation too quickly leads to a ferocious feedback response that quickly quenches it, like a fire that burns so hot it consumes all its own oxygen. But feedback is only part of the story. The ability of a galaxy to form stars over billions of years, rather than just in a brief, brilliant burst, requires a continuous supply of fresh fuel. This is where the galactic fountain and the accretion of high-velocity clouds become critical. The fountain cycle, driven by those same supernova, launches enriched material out of the disk where it cools and falls back down, effectively recycling gas. More importantly, the infall of pristine hydrogen from the intergalactic medium, in the form of those high-velocity clouds, provides the new fuel needed to sustain star formation over cosmic time. A galaxy that can effectively attract and capture this intergalactic gas can maintain its star-forming career far longer than one that is isolated and must rely solely on its internal recycling. The balance between outflow and inflow is a key determinant of a galaxy's long-term evolution. The final piece of the puzzle is the invisible hand of dark matter. While the interstellar medium is the visible fuel, it is the dark matter halo that provides the gravitational scaffolding for the entire galaxy. The mass and shape of this halo dictate how quickly gas can cool and condense to form stars in the early universe, and how efficiently gas can flow into the galaxy from the cosmic web later on. A massive, sprawling halo can draw in and retain a vast reservoir of gas, fostering the growth of a large, star-forming disk like the Milky Way's. The dark matter's gravitational influence also affects the internal dynamics of the interstellar medium itself, subtly guiding the motions of gas clouds and influencing the rate at which they collide and collapse. The large-scale structure of the galaxy, which sets the stage for all the small-scale physics, is ultimately a creation of its dark matter foundation. Unraveling this link from the micro to the macro is one of the supreme challenges of modern astrophysics. It requires building multi-scale simulations that can model the explosion of a single supernova, while also tracking the rotation of an entire galaxy over billions of years, a computational problem of almost unimaginable complexity. Each new observation, whether it's a detailed map of magnetic fields in a nearby nebula or a survey of star formation rates in thousands of distant galaxies, provides another crucial data point. They are all pieces of the same grand puzzle, revealing how the seemingly minor details of cosmic dust and interstellar chaos are, in fact, the fundamental forces that sculpt the majestic spirals and brilliant clusters we see throughout the universe, governing the birth, life, and death of galaxies themselves. But the influence of a supermassive black hole extends far beyond simple heating or cooling. It can fundamentally reshape the entire galactic ecosystem through its powerful jets. These are not gentle streams but tightly collimated beams of plasma and magnetic fields, launched from the poles of the accretion disk at nearly the speed of light and stretching for hundreds of thousands of light years. When these incredibly energetic jets plow into the interstellar medium of the host galaxy, they create enormous shock waves and carve out vast cavities in the gas. This is a double-edged sword on a galactic scale. Within these expanding bubbles, the gas is violently heated and evacuated, creating regions where star formation is utterly impossible for eons. Yet, at the edges of these cavities, the story can be completely different. The same shock waves that clear the interior can also slam into surrounding galactic gas clouds, compressing them to incredibly high densities. This sudden, violent pressure can overcome a cloud's internal support mechanisms, triggering a burst of new star formation in a dense shell around the jet's impact zone. We see stunning examples of this in galaxies like Minkowski's object, where a jet from a nearby active galaxy appears to have directly induced a wave of starbirth in its path. This creates a bizarre paradox where the same phenomenon that sterilizes one part of a galaxy can act as a midwife to creation in another, its ultimate role dictated by the precise conditions of the gas it encounters. This complex interplay makes AGN feedback a central character in the story of galactic evolution, particularly for the most massive galaxies. There is a compelling theory that this process is the long-sought solution to the cooling flow problem in galaxy clusters. At the heart of these clusters lies the brightest galaxy, often sitting in a dense atmosphere of hot gas that should, in theory, cool down rapidly and flow inward to form trillions of new stars. Yet we don't see this happening. The observed star formation rates are far lower than simple cooling models predict. The leading explanation is that the central supermassive black hole acts as a cosmic thermostat. As gas cools and begins to flow inward, some of it feeds the black hole, powering up the AGN. The AGN then responds by injecting tremendous energy back into the surrounding hot gas through its jets and radiation, reheating it and shutting down the cooling flow. This feedback loop cooling gas fuels the AGN, which then heats the gas to prevent further cooling, creates a self-regulating system that prevents the galaxy from growing impossibly large, and explains why the largest galaxies in the universe are not also the brightest star factories. Unraveling the precise mechanics of this feedback is a monumental challenge that occupies some of the most powerful telescopes on Earth and in space. Astronomers must act as cosmic detectives, piecing together clues from across the electromagnetic spectrum. Observations in X-rays from observatories like Chandra map the multi-million-degree gas and the cavities carved by the jets. Infrared and optical telescopes trace the distribution of warm gas and newly formed stars, revealing where the AGN's influence has either ignited or quenched stellar birth. Radio telescopes chart the faint, extended lobes of the jets themselves. By combining these disparate views, scientists can build a three-dimensional picture of how energy is transferred from the black hole to the interstellar medium. The goal is to create a universal recipe that predicts how much energy is required to halt star formation in a galaxy of a given mass, and how that energy is distributed between radiation, winds, and jets. This recipe is essential for our largest cosmological simulations, which rely on these subgrid models of AGN feedback to accurately replicate the population of galaxies we see in the universe today. Without it, the simulated universe looks nothing like the real one. Galaxies become too massive, too bright, and too blue. It is the fierce, regulating heart of the black hole that makes the cosmos look the way it does. For all the centuries we've spent unraveling the secrets of the interstellar medium, we are standing at the threshold of its most profound revelations. The next few decades promise a revolution in our understanding, driven by a new generation of tools so powerful they will feel less like telescopes and more like time machines, letting us witness the hidden choreography of gas and dust across the cosmos. This final mystery isn't about the medium itself, but about our own future quest to comprehend it. A future illuminated by groundbreaking observatories, unimaginably complex simulations, and a new way of seeing the universe that combines every signal it sends our way. Leading this charge is the James Webb Space Telescope, an instrument that has already begun to rewrite the textbooks. While Hubble gave us stunning visuals of cosmic landscapes, Webb is a chemist armed with an unparalleled sensitivity in the infrared. This is the key that unlocks the dusty vaults of the universe. Webb can peer directly into the hearts of the darkest molecular clouds, analyzing the faint thermal glow of the dust itself and the unique vibrational signatures of molecules frozen onto their surfaces. It's identifying the specific complex organic compounds, the alcohols, the sugars, the potential precursors to amino acids that form in these frigid nurseries. For the first time, we are not just inferring the chemistry of star birth. We are taking a direct inventory of the probiotic ingredients being delivered to newborn planetary systems, bringing us closer than ever to understanding the chemical pathway from stardust to life. But while Webb shows us the chemistry, another monumental project will map the geography. The Square Kilometre Array, or SCAR, is not a single dish but a continent-spanning network of radio antennas that will act as the most sensitive radio ear ever pointed at the sky. Its primary target, the faint 21-centimeter wavelength emission of neutral hydrogen, the most fundamental component of the interstellar medium. The SKA won't just detect this gas, it will create exquisitely detailed three-dimensional maps of its distribution and motion throughout our galaxy and millions of others. It will trace the faintest streams of gas flowing between galaxies, directly image the accretion of high-velocity clouds onto the Milky Way, and reveal the intricate filamentary structure of the cosmic web itself. It will be like watching the weather patterns of the entire galaxy, tracking the flows and currents that govern the galactic ecosystem in real time. These colossal observatories will generate a flood of data so vast that it can only be deciphered by their equally advanced partners on the ground, supercomputer simulations. We are moving beyond simple models of collapsing gas clouds into breathtakingly realistic digital universes. These simulations, running on some of the world's most powerful machines, now incorporate not just gravity and hydrodynamics, but also magnetic fields, radiation transport, complex chemical reaction networks, and the feedback from stars and supernovae. We can now watch in a supercomputer as a virtual supernova blast wave slams into a digital molecular cloud, tracking the enrichment of heavy elements, the destruction and formation of dust grains, and the triggering of a new generation of star formation, all in a self-consistent model. These aren't just cartoons, they are virtual laboratories where we can test theories of cosmic ray acceleration or magnetic field amplification with a precision never before possible, using the real data from Webb and the SKA to constantly refine and correct the physics. The ultimate future, however, lies in combining all these ways of seeing the universe into a single, unified perspective. This is the era of multi-messenger astronomy, and it transforms the interstellar medium from a backdrop into an active character in the cosmic story. Imagine a massive star collapsing in a distant galaxy, forming a black hole and unleashing a gamma-ray burst. We detect the initial flash of light with our gamma-ray and optical telescopes. But we also detect the gravitational waves from the merger, which tell us about the masses involved. Crucially, we can then study how the light from this cataclysm changes as it passes through the interstellar medium of its own host galaxy and then our own. The specific absorption lines imprinted on the signal become a forensic tool, revealing the composition and density of the gas it traveled through. We can even detect the high-energy neutrinos generated in the explosion, particles that travel in near straight lines from the source, largely unaffected by magnetic fields. By combining the light, the ripples in space-time, and the ghostly particles, we can triangulate the event with incredible accuracy and use it to probe the properties of the intervening medium across billions of light years. The interstellar medium is no longer an obstacle to be seen through. It is a lens to be analyzed, and multi-messenger astronomy gives us the prescription. This holistic approach will ultimately weave together every thread we've discussed, from magnetic fields and cosmic rays to dust grains and turbulent gas, into a complete tapestry of how our dynamic galaxy and all galaxies live and breathe. After an incredible journey through 29 profound enigmas, from the spinning diamonds that hum in microwaves to the fragile lithium that vanished from the cosmos, we finally arrive at the ultimate, synthesizing question that ties every mystery together. Is the interstellar medium simply a stage upon which the great cosmic drama of stars and galaxies unfolds, a passive and inert backdrop? Or is it, in fact, a lead actor in this play, an active, dynamic, and governing force that dictates the very rhythm and rules of galactic evolution? The evidence we've gathered points overwhelmingly to a reality far more complex and fascinating than mere emptiness. Consider the incredible agency we've discovered hidden within this so-called void. The interstellar medium is not a blank slate. It is a participant with its own physics, its own chemistry, and its own feedback loops. It generates magnetic fields that provide the skeletal structure for entire clouds, without which they would collapse in a chaotic burst. It forges complex organic molecules on the surfaces of dust grains, pre-loading new solar systems with the chemical prerequisites for life. It accelerates particles to near-light speed within supernova shock fronts, creating a pervasive haze of cosmic rays that influences chemistry and poses a constant, low-level radiation threat to emerging biospheres. It regulates its own temperature through a dizzying balance of heating and cooling processes, a thermal dance that decides whether a region will birth stars or remain a quiescent cloud for eons longer. Everywhere we look, the interstellar medium is not just being acted upon, it is acting. It is processing, transforming, catalyzing, and responding. This active role transforms our understanding of star formation from a simple story of gravitational collapse into a nuanced epic of regulation and feedback. Stars do not form the instant a cloud becomes too heavy. Their birth is a negotiated settlement between competing forces. The immense turbulence churned up by previous stellar generations provides support, holding back gravity's crush. Magnetic fields act as a brake, slowing the collapse and channeling flows of gas. And when stars do finally ignite, they immediately begin pushing back on the medium that created them. Their fierce radiation and powerful winds heat and ionize the surrounding gas, carving out bubbles and halting further star formation in their immediate vicinity. Their spectacular deaths as supernova then blast that enriched material back into the void, both destroying old dust and creating the conditions for new grains to form, while simultaneously stirring the gas into a frenzy that may trigger the next round of collapse elsewhere. The interstellar medium is not a passive fuel tank being slowly depleted. It is a complex, self-regulating engine. This perspective forces us to see a galaxy not as a collection of stars with some gas in between, but as a single, interconnected ecosystem. The interstellar medium is the circulatory system of this ecosystem. It transports energy from supernova across vast distances. It distributes the heavy elements, the iron, oxygen, and carbon essential for planets and life throughout the galactic disk, ensuring each new generation of stars is born from enriched ingredients. It breathes with fountains of hot gas flowing out into the halo and rains of cool gas falling back in. Its health and dynamics dictate the entire life cycle of the galaxy. A vibrant, star-forming spiral galaxy is one with a rich and cycling interstellar medium. A quiet, red and dead elliptical galaxy is one where this medium has been heated, ejected, or otherwise rendered inert, often by the colossal feedback from a central supermassive black hole. The fate of the galaxy is, therefore, written in the state of its gas. So the biggest unanswered question is not about a specific molecule or a particular physical process. It is about the degree of control. To what extent do these small-scale processes, the charging of a dust grain, the dissipation of a turbulent eddy, the chemistry on an ice mantle, orchestrate the large-scale destiny of a galaxy? Are we witnessing a universe where the tail wags the dog, where the subtle properties of the medium itself are the primary architects of the cosmic structures we see? Unifying these 29 mysteries into a single, predictive theory of galactic evolution is the grand challenge for the next century of astronomy. It requires us to draw a continuous line of cause and effect from the quantum behavior of a single atom on a speck of dust all the way out to the majestic rotation of 100 billion star spiral galaxy. The answer will determine whether we see the universe as a place where stars simply happen, or as a place where the space between the stars actively decides their fate. And so our journey through these 30 mysteries comes to a close, not with a final answer, but with a profound appreciation for the questions themselves. We began by gazing up at what seemed like an empty void, only to discover that the space between the stars is anything but barren. It is a dynamic, chaotic, and breathtakingly complex ecosystem, a cosmic laboratory where physics and chemistry operate on scales and under conditions we are only beginning to fathom. From the enigmatic hum of spinning nanodiamonds to the ghostly presence of dark matter shaping the galaxy itself, we've seen that the interstellar medium is the true protagonist in the story of our universe, actively governing the birth of stars, the formation of planets, and the very origins of life. Each mystery we've explored is a thread in a grand cosmic tapestry, woven together by forces both immense and infinitesimal. The fragile dust grains forged in stellar furnaces, the cryptic diffuse interstellar bands hiding unknown molecules, the violent stellar feedback loops that regulate entire galaxies, they are all interconnected. Solving one puzzle invariably leads to another, revealing a universe far more intricate and active than we ever imagined. This isn't just academic curiosity, it is the key to understanding our own cosmic ancestry. The iron in our blood, the calcium in our bones, and the very atoms that make up our world were all once part of this vast interstellar expanse, cycled through generations of stars and nebulae before finding their way into our solar system and ultimately us. The greatest takeaway is a fundamental shift in perspective. We must abandon the idea of space as a passive void. It is, in reality, a living, breathing entity. It breathes in pristine gas from the intergalactic medium and exhales enriched material through supernovae. It circulates energy through magnetic fields and cosmic rays. It experiments with chemistry on the surfaces of dust grains, preloading the dice for life. The rhythm of a galaxy's life, its star formation rate, its chemical evolution, its very shape, is conducted by the hidden physics of this medium. To understand the cosmos is to understand the space between the stars. As the next generation of telescopes and satellites comes online, from the James Webb Space Telescope peering into stellar nurseries to the square-kilometer array mapping the faint whispers of hydrogen, we stand on the brink of revelations that will undoubtedly rewrite our textbooks once more. The mysteries we've discussed today are not static, they are the active frontier of discovery. So the next time you find yourself under a clear, dark sky, take a moment to look up. Let your gaze settle not just on the points of light, but on the profound darkness between them. Remember that within that apparent nothingness lies a hidden universe of wonder, a realm of breathtaking beauty and deep enigma that holds the secrets to our past and the fate of our galaxy. Stay curious, follow the new discoveries as they unfold, and never stop marveling at the fact that we are beginning to understand this incredible